Very good morning to one and all. It gives me an immense pleasure to welcome foreign faculty Professor S.P. Gopal Madhubushi, Professor of Civil Engineering, Department of Engineering, University of Cambridge, United Kingdom, Professor Binod Kumar Kanojia, Director of Dr. B.R. Ambedkar National Institute of Technology, Deans of various sections, Planning and Development, student welfares, research consultancy, academics, faculty welfares, international affairs, and Professor Ajay Bansal, Registrar of the Institute, and Professor A.K. Agnihotri, Head of the Department as well as Course Coordinator, and Dr. K. Senthil, Coordinator of this course, and participants from various institutes as well as industries, fellow faculty members, and dear students. For the opening ceremony of GIAN course, dynamically loaded piles from failure mechanism to design, held from 18 August to 22 August 2025 through offline mode, organized by the Department of Civil Engineering, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. Now I request the dignitaries to come forward for the lighting of the lamp.
Hello, hello.
Hello, 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 hello. हाँ. heartfelt thanks to each of you for lighting the lamp. Hello. Hello. My heartfelt thanks to each of you for lighting the lamp and filling this occasion with light, warmth, and positive energy. I may request Professor Binod Kumar Kanojia, Director of Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, and Professor E.K. Agnihotri, Head of the Department, to welcome our foreign Professor S.P. Gopal Madhubushi with flowers of bouquet, shawl, and a memento as a token of love.
Check, check, check. Thank you, sir. Thank you, one and all. Am I audible? I think it's better without mic. I can speak. Okay. Yeah. I think without mic, I'll speak. And first of all, very good morning. And I would like to thank Professor Agnihotri sir for giving me the opportunity and considering me in this program. Of course, by man-made, it's a partial, it's a man-made, okay, but it's naturally occurs. For instance, I would like to say the earthquake, the landslide, the winds, storms, and somehow maybe the tsunami. Okay, let's say these four things. Maybe let's talk about earthquake. The earthquake is simply we can say it's a repeated loads. Okay, the repeated load cause the repeated stress to the foundation. It's a simple way. The repeated stress leads to the settlement as well as the damages, and finally also it's a failure. Okay, that's the reason actually we have to learn from the failure first, so that from the failure we can design the structure. Okay, and let's talk about the wind or storms. So wind, what will do? Wind will do like a highly, the lateral force as well as the uplift force. These two things actually significantly will generate to the foundation. So this creates either the settlement or the excessive stresses to the foundations. Let's talk about the tsunami. It is into the huge hydrodynamic forces that cause the significant bending moment and shear forces. Okay, so we have to take care when you design the things, when you design the foundations. And let's talk about the landslides. The landslides cause directly, maybe the rolling and falling of the rocks that creates the impact loads or dynamic effect significantly to the structure. So that is the reason actually this course is focused. So we have to see the failures and then we have to go to the design. So briefly maybe I would like to give why this course actually intended. The understanding the nature and the effects of these dynamic loads is crucial for designing the resilient foundations, okay, that can withstand such extreme events and especially ensuring the safety, serviceability of civil infrastructures. Therefore, the course focuses on understanding how piles respond, and maybe the piles or foundations or whatever it may be, when subjected to the rapid or cyclic forces, examining both failure mechanisms that may arise and the design approaches that ensures stability, safety, and serviceability. Also, to provide the participants with insights into the underlying physics of soil-wide interaction, methods to analyze the dynamic response, modern design strategies including liquefaction to mitigate the risk associated with the dynamic load. As maybe I am talking more about the structural dynamics, so the professor here, he will talk about the soil dynamics, and maybe I'm more of oriented towards the structure to structure interactions, but the professor will be more familiar with the soil structure interactions. Okay, thank you with this brief. I request Vikram to take over.
Now I may request Professor A.K. Agniutri, Head of the Department, to give a brief introduction about NIT Jalandhar and Foreign Faculty Professor S.P. Gopal Madhubushi.
Our young and dynamic team of teams and ISRA, dear colleagues, participants from different parts of the country, ladies and gentlemen, very good morning to all of you. Because this is first visit of, I think, any professor from University of Cambridge. So it's my duty to give some brief introduction of new entrance gate which is under construction. You must have seen while taking the round. This is our vision and mission of the institute. This is how our institution has grown up. In 1987, it was established. Then first batch was entered in 1989. And civil engineering started in 1990. First batch entered in 1990. Then in 2002, we got the status of National Institute of Technology. Earlier it was Regional Engineering College. In 2002, we got the status of NIT, National Institute of Technology. In 2004, MTech by Research program was started. Then in 2006, regular MTech programs in 8 engineering disciplines and PhD programs in all the disciplines were started. At present, 22 two-year MTech programs in engineering streams, MSc, Physics, Chemistry, Mathematics, MBA in Humanities and Management departments. 4 years integrated BSc B.Ed program under ITEP, and at present 14 B.Tech programs in different engineering streams, and also we are giving minor degrees in 13 departments. PhD full-time and part-time programs are also offered in all the departments. We see the ranking of NIR ranking 58 and total ranking of institutions on innovation achievements, that is in the range of 11 to 50. Outlook All India ranking 20th, All India ranking 22nd. World University ranking, we see US ranking, we are in engineering, we are ranked in band of 401 to 500. Institute campus is widespread over an area of 154 acres. It has many topographical features, various buildings of different natures with clean and wide roads surrounded by green belt. You must have taken round of the institution. At the center we have academic area, on one side boys hostels, on the other side residences and girls hostels. We have separate buildings for all the departments, modern AC classrooms with multimedia facilities, shopping complex, dispensary, post office, banks, stadiums, 10 hostels for boys, 4 girls hostels, activity in all the hostels, playgrounds and gym etc. for students, library facility, seating capacity 400 students new we have created where students can sit and study. We have named it Knowledge Center, recently constructed. Infrastructure facilities for students have been created like basketball ground with floodlights so that they can play after their classes are off. After 6 p.m. they can play comfortably. And upcoming infrastructure, mega hostel for boys, new hostel is coming. And G+8 story building with 27 lecture theatres, capacity 120 each. Air conditioned. This facility is ready, and only furniture etc. that work is pending. Within few days, within 1 month only, all these 27 lecture theatres they will be in working order. They will be operational. 14 are already there. Currently, we are 241 faculty members here. 43 professors, 58 associate professors, 140 assistant professors, 94 new faculty positions have been sanctioned, taking the total sanctions recently in our last board meeting about 50 board faculty members have been added. They will join within 1 month. Various departments, BTech programs, biotechnology, chemical, civil engineering, computer science and engineering, data science and engineering, electrical engineering. These are different departments and their intake. Total 1103 students intake at BTech level. Curriculum restructured to integrate 21st century skills, mathematical thinking and build the scientific temper towards a more holistic and multidisciplinary education, technology-enabled learning. Major academic initiatives under NEP, restructuring of undergraduate program as per National Education Policy, new education policy, which was introduced in 2020, we introduced in 2023. We have Master of Business Administration MBA also. We have signed MOU with ISB Hyderabad for joint programs, integrated programs, integrated BTech MBA joint degree with IIM Amritsar also. 4 years integrated teacher education program. Center of Excellence under PMJAY NIT is under process of setting up centers of excellence. PPC publications. Web of Science publications. R&D projects. In 2024-25, total number of 88 sponsored projects institute has received, and total number of funding agencies 24, and total amount sanctioned is 55.22 crores in last year only. These are some initiatives which have been taken for our students to help them. Now, in-house ERP system has been, why I am showing this? Because other institutions, if we see, they have spent crores of rupees in developing this ERP system. They have paid 2, 3, 4, 5 crores to the different agencies for ERP system. Here, under the able guidance of our director, he is basically, sir, he is professor in School of Computational and Integrated Sciences at Jalandhar University. So that is visible from his vision. He has developed all ERP system in-house without spending any money. Of course, with the team of these very vibrant and very young teams and our registrar. They are very supportive to him. They are helping in all respects. Under his able guidance, we are able to achieve so many other milestones. And this ERP system, this is very important because earlier what we were doing, we were collecting the data in hard copies, files were created, at the actual time of showing to somebody, it was not available. Now everything is available at one click. All question papers, they are available on ERP. Their solutions are available on ERP. Even assignments are available on ERP. Starting from students' admission till their degrees given, and even after that, if they need any certificate, whatever they need, every request they can make to ERP. So everything is now on ER, online system. And why I am showing this mainly is that everything has been created in-house. No money has been spent. Only under our director's guidance and leadership, and with the help of these young team of deans and registrars. Online admission portal, tabulation of academic portals, all students' feedback that is available online, and students' feedback on outcome of each course that is also available online. Online no dues portal, otherwise students were wandering here and there just for getting no dues. Now everything is online. Equipment, whatever equipment is available in any of the department, now equipment booking portal has been created and list has been shared with everybody, so people can book and use the equipment turn by turn whenever they get the chance. Sir, this is our placement scenario, last year's placement. We have incubation and entrepreneurship, TBI, Technology Business Incubator, Space Technology Incubation Center. So this is some brief introduction of our institution. Now, I have also been asked to give some brief introduction of our esteemed speaker for this course. He needs no introduction. It's like saying he is professor in University of Cambridge. I think that information is sufficient. That US ranking of, if we see US revert, US ranking of University of Cambridge, last 3-4 years it is 3, 4, 5 like this. So from such a prestigious institution, he has come, he is professor, full professor there. I think this much is sufficient. But still, as a protocol, I will read out some brief. Professor Gopal Madhabushi, FR Engineering. He is fellow of Royal Academy of Engineering, UK. Again, I must say that this FR Engineering is sufficient for his stature. FICE, Professor of Civil Engineering at University of Cambridge, UK, and the Director of Stockfield Center. He is Professional Fellow of Day1 College, Cambridge. He is the Head of Geotechnical and Geoenvironmental Group of the Department of Engineering at Cambridge. He has over 35 years of experience in area of soil dynamics and earthquake engineering. His expertise extends from dynamic scientific modeling to the time domain finite element analysis of earthquake engineering problems. He has an active interest in areas of soil liquefaction, soil structure interaction and liquefaction resistant measures and their performances. He has an active interest in the biomechanics of HIV replacement surgeries, hip replacement surgery. He has acted as an expert consultant to the industry on many geotechnical and earthquake engineering problems. For example, Mont McDonald, Royal, Haskoning and Rampol, Italy, Offshore Wind Logistics Limited, UK, Adani Green Energy Limited, India, etc. He has an active interest in post-earthquake reconnaissance work and has led engineering teams from UK to 921, GIAN earthquake of 1999 in Taiwan, the Bhuj earthquake of 2001 in India, and many other missions. He has served as the chairman of earthquake engineering field investigation team that runs under the auspices of Institute of Structural Engineers, London. He has awarded the TK SE Award in 2005, 2010 and 2013 by the Institution of Civil Engineers, UK. The BJ Medal in 2010 given by British Geotechnical Association. The Shamsher Prakash Research Award in 2006. Medical Innovation Award in 2007. The IJS Civil Pioneer Award 2008. Bill Curtin Medal in October 2009 by the Institution of Civil Engineers, UK. IJS Dr. Shamsher Prakash Award in 2017 for his contributions in the area of soil dynamics, tsunamis and earthquake engineering. He has 215 plus journal publications and 320 plus papers in international conferences and workshops. To date, he has authored a very successful book on the design of pile foundations in liquefiable soils, Imperial College Press, and geotechnical chapters in the book on designing through Euro Code 8 tailors and trances. His new book on centrifugal modeling for civil engineers has been published by Spawn Press or the Taylor and Francis Publishing Group. This is brief biography. I am very thankful to you, sir, that you have very kindly agreed to deliver lectures in offline mode and visited our institution. From last 2 years, from 2023, I was trying. Ultimately, in 25, I got this success, and he is here. Thank you so much.
Thank you, sir, for your brief introduction. Now I may request Professor S.P. to say a few words on this.
It's okay. I think I don't know this side, my voice is being everybody can hear me?
Yes.
Good. I'm overwhelmed this morning. It's been a real pleasure. I also had the time over the weekend to spend some time walking around the institute. It's beautiful. We're really lucky to be here, both participants and students here, participants of this course, as well as the students and faculty. You very rarely get to go to a place and get a feel for the place so quickly. Everybody here is so welcoming, and so far it's been a total pleasure for me. Professor Agnihotri has just mentioned that he's been asking me for a few years. It's not the lack of trying, or I'm not playing. I wasn't playing hard to get at all. It's just that the timing worked out. But I remember I must have met Professor Agnihotri maybe more than 10 times at different conferences, various other occasions. He would always come and stand to, my left eye is not very good, so he would always come and stand behind my right shoulder and wouldn't say anything. And I would tell that, Professor, you promised you are going to come to NIT Jalandhar. Yes, I will come. And he persuaded me, applied the paperwork for the GIAN course, and I just had to provide the most basic information, and he sorted it all, and here I am. It's a real pleasure. I don't want to say too much, but talking to your director and other deans and so on this morning, I get the feeling that this NIT Jalandhar will be going places, because to run an institute like this, in my opinion, you need a dynamic leader followed by supportive academic collaborators. And I think you've got all the right ingredients. You've got great infrastructure, great team, and all that we need is top-notch students who are interested to learn. And learning is the most important thing you need to focus on. And hopefully in the next 5 days or so, you'll be sick of seeing me be talking too much. But one thing I'd like to focus or start by saying is that it's not about equations, it's not about theory, it's about understanding. Once you've got the understanding, everything else will fall into place. And that's why we title the course as From Failure Mechanisms to Design. Because if you understand understand how something can fail, we as good engineers should be able to design things to resist that failure mode, and therefore we'll make resilient infrastructure. That would be the theme. But for that, the key component is to understanding the failure mechanisms. And for unusual loadings like earthquakes and tsunamis, like Mr. Sandhu was saying earlier, you really need to know where this load is coming from and what effect it will have on a given infrastructure. One other point I wanted to say is that there is a draft schedule that was prepared. We will try and cover all the bits that we said we will cover in that, but also provide some additional lectures. I think we've got sufficient time to be a bit more flexible. But I'd like to kind of take you through some of the processes of the research that we undertake that leads to the conclusion and the results we get at the end. Without knowing the methodology, it becomes difficult. It's not as attractive. If I say, here are the results from an experiment that was done before, it's like watching a cooking show and they'll say, here is the recipe. By the way, if you follow what my instructions, here is the nice looking jalebi that came out. You need to actually see the person go around, how the frying goes on, and the rest of it, and see how the jalebi is made. For eating, the final product is okay, but to making again, you need to know the process, right? So we'll follow that particular strategy and we'll go through the course in that. So be flexible, relax for the next 5 days, and I'll entertain you, Professor Agnihotri will entertain you, and come with an open mind, and the rest we will take care of. Okay? And again, I'd like to thank for this fantastic welcoming function you guys organized. It's been a real pleasure to meet you. Thank you.
Thank you, sir, for your insightful thoughts and views. Now I request Professor Jalandhar to register of this person to say the notes on this program.
A very good morning to all of you. Honorable Director, sir. Professor S.P. Gopal Madhushi, Professor from University of Cambridge, UK, my fellow colleagues, and dear participants. GIAN programs are not the ordinary programs, they are meant, and in fact, they have been conducted from a different perspective. There have been so many faculty development programs, short-term courses, and courses of other nature, but GIAN program is having a different kind of structure. If you look at the schedule, probably, I hope that you must have got that. Lecture schedule is not too hectic or too busy. Only a few lectures, maybe 2 to 3 lectures per day will be there as far as my understanding goes. But that doesn't mean that the rest of the time you cannot utilize for this purpose. In fact, respected professor will be here all the time, and it is expected that you will interact on the specific issues which cannot be taken up in the class as such, and you will approach and clear your queries if you have any. I am basically a professor in chemical engineering, looking after by chance the charge of registrar, but I have special affection to civil engineering. I recall a previous program that was conducted there in the civil engineering department. Professor Agnihotri was the coordinator. That time he was officiating director also, so I got the chance to conduct it physically. The program was on landfills, so that happened to be my area of interest as well. And Professor Krishna Reddy from University of Illinois, Chicago, he came here. I would like to go to the words initiative on academic networking globally. So that course was truly conducted with the perspective to have a networking. We were so glad, we were so happy to have Professor Reddy, and he actually initiated at that very program a concept of EGRWSE. I hope you know that is a well brand name in your domain or in your branch. And it's an international conference, and probably 5 to 7 its versions have taken place. 2 of them had happened at NIT Jalandhar, and rest all at different places like Turkey, Spain, and the next version, as I know, is at NIT Surat. is what is called networking. You had the networking, and Professor Reddy had been guiding us on various occasions, at various times. So that kind of expectation is also there from this course as well, that we have the networking. Because in 5 days, what I understand is that we can just initiate the idea of a particular topic, but go into the depth will actually will depend upon the interest of the individual, how far you want to go into the depth of the subject. But just possible that only initiation has been done right now, but the true thoughts or queries or some other things come in your mind later on when you are deliberating on the issue, but whom to talk to at that time, because the course will end in 5 days. That then if you have the networking, if you have the grouping, I would say you have the grouping with networking with professor from NITs, and grouping among us yourself as well, so that whenever a similar issue which needs some kind of discussion or deliberation comes into your mind, you have somebody to talk to. So that is what I feel that this course is meant for. I am not a subject matter expert, but what I can see from the title is very, very relevant from today's perspective, when we see that so many landslides and other things are happening, that how to have a strong, rigid structures, what I can say is, even in our, what you say is the 3 essential things normally called as roti, kapda or makan. I would say makan as an infrastructure, not only makan, but there are so many other things involved into that. The infrastructure is very, very important part for any individual and for the growth of the company as well. Sir was only talking a few minutes earlier that suppose if a bridge gets collapsed, how much havoc or how much disaster it can cause actually. So we cannot actually afford to have that kind of unforeseen collapses at any time. After a particular life of the bridge, it has to be respected, it's okay. But it has been constructed today and going collapsing in say a couple of years or after say 5 years, it's not in the interest of anybody. So I think this course will talk on that. I'm not expert, I am answering. I wish all the very best to the participants. I wish that the stay of Professor Madhushi will be a pleasant at NIT Jalandhar, and we will have long association beyond the course conclusion, and look forward that something concrete comes out from this course as well. Thank you all.
Thank you, sir, for your insightful thoughts and views. Now I will request Professor Director, to say a few words at the opening ceremony of the GIAN course.
So good morning, one and all. So I think that Professor Anurtri and Professor Ajay Bansal and our expert, they have already discussed a lot of things. So, but only we have seen that in the GIAN course. No? So the topic is taking that failure of mechanism of a design. This means that you should start your thinking where is a problem. Where is a problem? What solution you will provide. So as a director of a NIT Jalandhar, I think that the role of a director is only the facilitate of a student and faculty, or solve the problem, nothing else. That is my observation. So similarly, the faculty of a civil engineering department, they have taken the topic of a failure of a mechanism of a design. I think that we should focus that what calamity is there across the world. So how we can solve the problem? In that time we see that different countries facing a different calamity of regarding of a building collapse and earthquake. So how the problem will be solved? I think that is a challenge for as an academician. So Professor Anurtri has discussed that a collapse of a bridge and collapse of a building means that nobody is taking as a design part of a take a responsibility. This is my responsibility. The building is collapse and bridge is collapse. I think that in an honest way we should take our pillar of a responsibility. Then we can learn, start. So even that if you solve any problem for a society, that's really a very wonderful. Means that as an academician, we should try to solve some of the problem. Regarding of a institute, we have seen that in a lot of things we have discussed that we discussed that because of some of the participants have gone outside of that NIT Jalandhar. So I think that you should learn that where there is a difference. Professor SP Gopal Madhusi is from Cambridge University. So what exactly, either from this institute or some of the other institute, what exactly the difference is there? So either a teaching difference or critical thinking difference, and Professor Madhusi has already discussed that we should not learn of that equation. We should not learn of the theory. What critical thinking is there? Suppose the current situation is different, and after 1 year situation is different, you should think and try to solve it. That is critical thinking. So you should think that how the teacher is teaching, how we have grasped that is a knowledge, means that how you are thinking in critical to solve the problem or technical design of the problem. So I think that you should learn within 4 or 5 days. So what exactly the difference between our teacher and topmost university teacher? So I think that there is a very good interaction if you see that what exactly difference in teaching, critical thinking, how the university comes in that number. We are discussing of in global ranking in 3 4. I think that credential can be achieved by the some of the faculty member and by the students. That is a university is important. So I think that this course in GIAN course, you have seen that in the government of India Ministry of Education, they have received. Dr. Kansal has already discussed that in networking. That networking is a one part. Our students, they can see that what exactly difference in our institution, what is the difference between our global institutions. At the time of a discussion, at the time of whatever you have learned, so you can see the difference. So that's why I think that in a GIAN course, this is a 9th or 10th GIAN course in NIT Jalandhar for this year. So I think that our student and faculty, they can also learn that how we can teach, how we can insight of our students, they can think beyond of only the classroom. So I think that we should learn from an expert. So you should create of such environment in a 5 days. You should take even that at a time of a morning interaction with the Professor Gopal. We have discussed that after 4 or 5 days, we want to meet you what exactly is the difference in education in your institution and our institution, how we can come up with a huge problem. So I think that good interaction, and you should enjoy for 5 days. And Professor Gopal has already discussed that you should relax in a 5 days, not a day tension. So I think that you can more think critically when you are relaxing. So my observation, because that is not my field, so I think that we should not waste our time. Even that at the time of a discussion, we have some of that legacy to start up any program. So even that we should skip off of each program, whatever each need is there, only we will take only that movement. Otherwise, we should give more time to discussion of the technical things. That is our observation, that more focus on technical and less spend of time on physical. So I think that you should enjoy of a 5 days, and you should discuss Professor Gopal. I think that our student as well as the faculty member, those who are participant from outside of a NITJ, either inside of a NITJ, they should decide how you can reach of a in a good university, how you can go in that. That's it. I think that you should introspect yourself and how you can grow in a contribute for a society. I think you should enjoy your 5 days in NIT Jalandhar. I think that our team is here for the boarding and launch. Thank you all the best.
Thank you, sir, for your insightful presence. Now I request Dr. K. Senthil for
Thank you again for anchoring the wonderful session. I express my deep thanks to Professor Ambedkar, Director, NIT Jalandhar. Without his permission and constant encouragement, this course will be possible. I would like to thank Professor Gopal for his concern as well as agreeing for offline course, and I further express my deep thanks to participants from various industries, especially industries like ONGC, Day1, MES, SPS Civil Infra Private Limited, and some of industries as well. Maybe they were not present here. And there are many institutes, especially like to thank or highlight ID Bombay, the participants from ID Bombay, ID Roorkee, SK Surat, CBRI Roorkee, JNT Hyderabad, JNT University Hyderabad, GNDC Ludhiana, Amritaveni College of Engineering Maharashtra, and PEC Chandigarh, KK Institute of Engineering Education and Research Maharashtra, Khalsa College Engineering Technology Ambedkar, DAM University, and MCP College Jalandhar. And I would like to extend my heartfelt thanks to GIAN coordinator ID Hyderabad as well as the local coordinator for their team for their constant support in organizing this course. And my sincere thanks and appreciation goes to the Bigred, Ria, Pali, and also Pavan as well as the Sonu Kumar for their support and organizing these arrangements. And those dedicated efforts made arrangements of this course possible. I am also grateful to the fellow faculty members, colleagues for active participation, which added great value to this program. Finally, I would like to acknowledge the state office for their constant support and getting all the privileges and the last 4 or 5 days valuable assistance. Now I request you all for the nation of the peace.
We are trying to train civil engineers in a changing world. Our role continuously changes. It's like what was a problem 30 years ago, big problem 30 years ago, is no longer a problem. And what is problem today may not be the problem in 30 years' time from now. So we need to really be adaptable, remembering we are there to serve the society. So the subtext is the observed damage and lessons learned from some of the recent earthquakes. And as I said, it falls under the title that we want to try and design these pile foundations to withstand extreme loads and like dynamic loads. And therefore, it is relevant that we look at how some of the damage is. So this first 1 hour of lecture, 1 hour, 10 minutes to 20 minutes, all I want you to do is to look at the pictures, relax, and listen to what I'm saying. Okay? You don't need to take any notes. We're not going to come back to this and ask you funky questions later on in the course about this. First hour is free. Just relax and see why civil engineering is interesting. The picture there down has become both symbol of development and also a lot of politics in the UK. It's called a HS2 project, and different governments come and say we are going to build HS2, and then later on they'll look at the cost and maybe not in the next 2 years. And it's become, but demands quite a lot of changes in the way we do engineering. Okay, just for this lecture, let me introduce what do civil engineers do and how can we be transformative for the society and what do we mean by resilient infrastructure. And we take the definition of resilient infrastructure within as that which can withstand extreme events, for example, earthquakes, tsunamis, volcanic eruptions, flooding. And I'll show some examples of each of these. More importantly, if I want to study these kind of extreme load events, how do I go about doing research? How do I, these are extreme events, so they're not going to happen every day for me to instrument a building and see how it performs or do things like that. So we need to have some research strategy. And once you kind of are able to create that, how do engineers then go about creating some infrastructure that is resilient to these extreme events? And I'll try to summarize, and I'll be happy to answer questions. I've been teaching for the last 35 years now, so at any point if you feel I'm not sure what he's on about, put your hand up and ask me. And that won't throw me off my lecture, and I can always go back and restart where I left. So feel free to do that at any point. Some history, right? 200 years, the Institution of Civil Engineers has been in existence in the UK. And in 2018, we celebrated 200 years. Now it's been another 7 years, so it's 207 years to be up to date. There are few key civil engineers who played a role, who are not actually, they never call themselves civil engineers, although they founded the Institution of Civil Engineers. One is Brunel, you may have heard of him. Isambard Brunel is a famous engineer. He built everything from ships to trains. He had invented a different gauge, not the broad gauge, but broader than the broad gauge lines in the UK to improve the comfort for the passengers. By the way, all of that was done with private money. No government money was invested initially in railways in the UK. He used to go and raise money from investors and construct a railway and promise a dividend for the money at the end. So he's a great entrepreneur as well. And on the other side is a man called Bazalgette. Bazalgette, they say, has actually saved more lives in London compared to anybody else, all the doctors in the UK put together. Why? Because he came up with the sewerage system in London, which kind of reduced the outbreak of cholera and other communicable diseases. So, as a civil engineer, he saved more lives than all the medical doctors put together. And that is some number to remember. So, civil engineers can have a big role to play. I'm going to pick on the bits Brunel has done in terms of tunneling. This is back in the day in 1700s when people didn't know what tunneling was, right? They were very scared. And this man then comes up with and constructs the first tunnel below River Thames. Okay, this is going through London Clay before River Thames, and he started that in 1826 and it got finished in 1847. He had to come up with so many different things, like how do you support the tunnel after it's constructed? How do you support the face from soil falling back into the workers? He has come up with ideas like this, where he would create a box. Each box is big enough to hold a man with a pickaxe, and they would excavate the clay in front of them. And like that, they constructed the tunnel layer by layer going forwards, and all by hand. And they were very worried that the Thames River, which is above, but he made it work. Then the tunnel finished, and nobody was using it because they could see the entrance was on the left bank of the River Thames, and the exit was on the other side. So they knew the thing was through, but they also knew it was going underwater. They thought, oh, this might all leak water at some point and we'll all get drowned. So nobody was using the tunnel. Then he came up with this idea that he will hold a banquet in the tunnel. You can see the picture here, and invited all the big and mighty in London to come and have a dinner in the tunnel below River Thames. And once that has happened, then people started using it slowly. So he had to not only make the structure, but prove to the society that it's actually safe. And then subsequent developments, they started putting these steel linings around it, and this the so-called tunnel shielding started, and that was done by a man called Greathead. If you go to Institution of Civil Engineers in London, it's next to Big Ben. You can't miss it. You can go and look at some of these really great names from Arab to everybody listed there. Coming back to Basel-Z, the old Basel-Z sewers were all constructed by brick, and these are all still operational, and they are now slowly running out of capacity. By the way, the same British also created the sewerage system for Bombay, right? And it kind of to remove the flood water as well as the sewerage from city of Bombay. They have designed it so well that it lasted nearly 100 years. And I don't know whether we actually added any more sewer lines in Bombay, but given the floods, I just was there in 2 days ago. How much rainwater is everywhere stored? My guess is not much. So engineering means you got to solve problems, and you must have the foresight to size the things appropriately. Anyhow, this man did the London tunnels. As I said, they're still operational, and the network is quite vast. This is the map of London, where he managed to get the sewer water out of London into Thames using these tunnels. So those were the challenges in 1800, right? So old tunnels for transportation of people, water, and sewage, right? And as a result, London continued to grow, and in fact, it is still continuing to grow today. It's about 20% of UK population lives in and around in what we call Greater London area. That is, 1 in 5 British people lives in London. So the rest of the country, they are only vastly spread out. In Scotland, which has more than maybe 40% of the land area, has a population of something like 6.5 million. So it's really sparsely populated, and it's also very cold up there. Now, our challenges are now changed compared to 1800s. Now we have to do things in the backdrop of, say, climate change, rising water tables, and other risks, some of which I will talk about. So modern civil engineers need to innovate in delivering the solutions that are required today. This infrastructure that we need today is very different from what was needed back in 1800s. So I'm going to pick a couple of examples of more recent projects in London again. So this one is called Crossrail. Crossrail basically was funded because we have Heathrow on the west of London, and the banks are all located on the east in a place called Canary Wharf. And the reason for Crossrail is, apart from providing transport for other commuters, really how can we get these bankers quickly from Canary Wharf to Heathrow so that they can fly to Frankfurt and do financial deals. Most of UK money comes from service sector, that is financial service sector. So the consequence of that is that we needed this Crossrail. But if you heard about London, we already have quite a lot of tunnels in London. So this new tunnel had to go below all the existing tunnel lines. So suddenly we were faced with problems like what will happen if I make a big, the diameter of this tunnel is about 8 meters. Okay, it's fairly large tunnel, and two of them, upline and downline, and you needed to worry about the tunnel going below pile foundations of existing buildings, or the tunnel actually crossing other metro lines already there. We already have 3 levels of tunnels for current ones. This one had to go below all the existing 3 lines. So how do you go about it? So they had some shafts at Bond Street and other places. I'm not going to focus too much. And this Pudding Lane portal is the important one. And they had to put shafts here. Forget the name places. I'm going to show you. So first thing, to make a new tunnel, you need to make a vertical shaft that goes into the ground. So this is the plan view, and you're trying to create a circular shaft to drop your tunneling machine in. So the size of the tunneling machine is about this. This is the 8 meters in diameter, and you can see the cutters and fluids that you need to inject to treat the clay so that it comes out as a flowing liquid, so that you can pump it out. So this whole EPP, the earth pressure balancing machine, is a fairly complicated beast, and it needs to be lowered into the ground. So you take this and then lower it into the shaft, as you can see here, and so they then land at the base, and then they can start tunneling horizontally to create the tunnel itself. And you also line the tunnel as the tunneling machine goes. So there are 2 machines. One obviously is called Elizabeth, the other one is called Victoria, which started doing this back in 2012. So they were creating tunnels basically like that. At locations, you will have a cross link between the tunnels, and that is a safety feature. The same thing exists for channel tunnel as well, if you know about that. So you got individual tunnels, but at some spacing, you will connect them below. But this is also a good picture. It kind of shows how many other things are there which this tunneling machine has to avoid when it goes through. So this is what real civil engineering is. How do you visualize this? How do you track what is already in the ground, and what is the effect of making a new tunnel in ground on the existing structures? Because if you are the owner of the building on the surface and a new tunnel is built below, and that causes settlements or cracks in your building, you'll go and sue the tunneling company, won't you? Obviously. So you need to be responsible that that doesn't happen. This is a very old slide from my colleague and former professor Robert Mayer, and he looked at this tunnel collapse mechanism. I think he's done his PhD in 1974 or something like that. And as a result of this one slide, he became very famous, started his own company called GDG, and they are the consultants world over at the moment. To, if anybody wants to make a tunnel or have problems with tunnels, they will go to GDG in London, and he owns the company. So this is a very powerful slide. What he has put in his PhD thesis made his career lifelong. And what he was doing is he tried to do centrifuge modeling. I'll come and explain maybe tomorrow what centrifuge modeling is and how we do that. But basically, it's a realistic way to model what happens. And he could create the tunnel and observe how the collapse happens in an experiment, and what will be the consequences for the structures on the surface. So this ground collapse is a very big problem, especially when the tunnel goes shallow. Deep tunnels are generally more safer than shallow tunnels. And on the ground, if the tunnel collapse happens, and that is not just an experiment, things like this happen as well. This is in Munich, I think, somewhere. And this kind of sinkholes open up, and a bus was going. Suddenly, this opened, and the thing fell in because they were trying to tunnel underneath, and this whole ground has fallen into the opening that the tunnel created. It's not just limited to the Germans. We have our share of disasters, and this tunnel collapse happened on when the Heathrow line was being built, Heathrow Express line. And the only thing that was funny about this tunnel collapse is the buildings, the porta cabins you see there belong to a company called Balfour Beatty. And their own, because they didn't do the calculations properly, this collapse happened and their own offices got destroyed. So there is some justice. If you don't treat ground properly, it will come and bite you on the backside. Here is another example where they were trying to tunnel below. It's next to a railway line, and you can see the big sinkhole that has formed. And these things happen if you're not careful. The most famous one in our part of the world is this Nicole Highway failure in Singapore. And this happened not so much because of the collapse of, they were not tunneling here, but it's a miscalculation by the engineers who created the support. They were trying to excavate on the side of the Nicole Highway. This is as part of making better connection to Changi Airport in Singapore. And suddenly this whole thing failed, and you can see the road got destroyed. The only reason more people didn't die is because if you look at the far end, there are traffic lights there, and they were red at the time when the collapse happened. Because they were red, all the traffic was held behind, and so that's another reason why we should not ignore the red lights and go through red lights easily. And luckily, casualties were less. But this went, Singaporeans are very, very strict about health and safety and everything else. So this went up to the highest levels in Singapore government. Robert Mayer, the GDG were consultants on looking at the collapse. He was on the committee and all that kind of stuff. But really, if you don't understand the mechanics of the soil mechanics properly, things like this can happen. Okay, those are the bad things, right? What can we actually do? I'm going to give you an example of a Jubilee line extension. And the Jubilee line extension happened maybe 10, 12 years ago now. And this picture you should recognize. This is the Big Ben. And this is our parliament, British parliament, right? So opposite this, they wanted to create a new, the Jubilee line runs underground below. So this is River Thames, and the line kind of runs in that direction, okay? And the station is just here. And, if you go now, the construction obviously is finished long time ago, but they left the props in place, and you can still see them. They made it part of the architecture. Normally, props you take off after construction, but in this case, they made it part of the design. So, before they started constructing this, the companies which were in charge of design and build had to sign in contract with their names on it that the settlement of this old masonry structure will be less than 50 millimeters. The diameter of the tunnel they were creating below was about 10 meters because it included a station box. So you're trying to make a hole about this big. And you got this old heavy masonry structure above you, and you as an engineer need to sign on a piece of paper that because I am making the hole, the structure on the top is not going to settle more than 50 millimeters, and 50 millimeters about that big. Because this structure can only tolerate that level of differential settlement. Anything more than that, it will crack up, and half the tourists won't come because most of the people who come to London want to see the Big Ben. If it is all cracked up, nobody will come. And of course, they said we will do it. And then the newspapers got in wind of this and started putting headlines like this: Tunnel may give Big Ben the pizza tilt. everybody knows what Pisa Tower is, and they started publishing. This is the Evening Standard, which is kind of slightly tabloid newspaper, but they put that next to the Big Ben and say, oh, it's all going to go tilty. There were Sunday Times following. They also came up with something similar. What they are trying to do. Here is the tower, and here is where the tunnel is going to go. This is a very big hole people are trying to create, and therefore this whole thing is going to tilt this way. Yeah. So that is actually what the plan was. That there is the Big Ben. This is to scale, and this is the Jubilee Line Extension Station, and that is 3 levels. So you got the station area at the ground level, 1 level below to cover link to one layer of tunnels, and another level below to another line. Okay. So these are big civil engineering projects. What they came up with is this tube mache technique, where you make a hole in the ground, a shallow hole, and you inject tubes across and pump grout. And the idea is, as they would observe the tower, and as soon as the tower starts to show some settlement, you will pump grout at high pressure to try and hold it in place and stiffen up this clay. And the actual tunnel goes somewhere below. So you need to inject this grout layer between the tunnel and the structure you are trying to protect. That is the plan, right? And the expected settlement was basically this level, whereas the severe settlement without any compensation grouting is this level. And this is not acceptable, because you already signed the contract saying my structure is not going to settle more than 50 millimeters. So this is the layout, and obviously quite a lot of injection points are shown in blue, and the shaft is over there. And initially, as soon as the tunneling machine arrived below, they could see settlements, and the very initial settlement they got is of the order of about 20 odd millimeters. So you already, I'll show it to you. Yeah, so the tunneling started, box excavation started here, and in November 94, by 95 you got settlement of almost 15 millimeters. And the tunnel didn't a bit, and then settles a bit, raises a bit. So they could had grouting episodes, global warming, but here are some pictures, right? These are pictures taken from exactly the same spot, 1928 and 2004. And that is the glacier, and here is what you got today. Completely the ice cover has disappeared, and you got these glacial lakes with glacial till underneath it. Same thing in Switzerland. This is a mountain. It used to be like that, and if you go today, it will be like that. And clearly, if anybody says these are not our government at the time to compensate for this. You have mining issues like open channel mining, which you can see clearly. Things like this, California mining waste being transported, and so on. So all these are engineering challenges. And if you think that civil engineers have no role to play anymore because we know how to make concrete, you're, I'm afraid, sadly mistaken. Because making concrete is not the issue. Solving problems is the issue. And problems are continuously changing. That is the main point I wanted to make. Now I move on to a little bit closer to what we will be talking in this course on resilient structures against earthquakes. This is a building that has perfect structural engineering. Senthil Sab has done a great design. No problem with the structure, right? However, the whole building is now on its side because the foundation has liquefied and the whole thing has fallen. Nobody is going to use the structure. No point how well you make the structure if it is going to be at 60-degree angle to the ground, right? So in the end, the structural engineer will always blame the geotechnical engineer and say, you guys don't know what you're doing. And there's some truth in that. I will show you some of the pictures. These are the Haiti earthquake that I have taken a team to, and that is the presidential palace, which itself has collapsed in Haiti, Port-au-Prince. And the amount of, I mean, this is just one picture. You could take picture any direction, anywhere, you would get exactly the same thing. Even old churches which have seen previous earthquakes have collapsed. This is our own famous Bhuj earthquake, where the streets of Bhuj were looking like this. This is basically completely rubblized the houses. This is with not any great pleasure. We started a visit, a technical visit from Ahmedabad. Ahmedabad is 350 kilometers from Bhuj. And no matter how strong the earthquake was in Bhuj, the buildings in Ahmedabad should not have done this. Whereas they had at least 30 odd buildings that collapsed. And this is the famous Mansi building. There used to be another building next to it, which you can no longer see. And there are these stairs which were connecting to the other building. As that building went down, you can see these are upside down stairs. No engineer is going to make stairs that way, right? You can't climb the stairs upside down. But that's because this was attached to the other building, and as it went, you can see it was not great. And you could, I mean, this is a structural engineering problem. Beam column joints seems to be a specialty of ours. We can't seem to put enough shear reinforcement between beam and column. And again, I'm a geotechnical engineer, but I should know enough structures to say, looking at it, yeah, it's clearly there's no shear connection between this and that. And as the thing started to shake and open up and close, you can see where the cracks are happening. This is what you call pancake collapse. You lost a floor underneath. Typically, buildings in India, you open up the ground floor, put pillars, remove even one pillar, and create showrooms. Because ground floor means showrooms for us. And it's all fine normally. When the earthquake comes, you'll get found out. And that's what happened to these buildings. I hope this place, now with the advent of, I mean, we used to go on site visits and see like that, but now you can actually, so many mobile phones are there, and you get images like this. This is a Mexico City earthquake in 2017. People are there still, they're feeling the shaking, and the building collapsed right next to them. So now we are getting to see actual failures happening in almost in real time. Now, we'll try and I'll try and steer you more towards soil liquefaction now. You got what's I'm going to try and keep it as simple as possible to start with. What is soil liquefaction, right? So, as an undergraduate, we all would have done this shear box experiment. It's almost the first or second lab you would do in any geotechnical course, right? All you're doing is you got a box which is a split box, and the top of the box can move relative to the bottom. That's all it is. You fill your sample, and the shear plane always will be where the two boxes can slip. So that is marked by the dense sand. You apply some vertical load and a horizontal load. So you move the top of the box relative to the bottom. Easy. So if I can organize the soil inside either in a loose pattern like that or a dense pattern like this. So if I packed it quite loose, when I shear it, the balls can all fall into the gaps in between. So I'll get a reduction in volume, what you would call volumetric contraction. If the balls are already in dense packing like this, when I shear, each ball has to ride on the next one. So the overall volume increases. And that's what you would call dilation. So loose sands contract, dense sands dilate. How does that manifest? If I were to plot the shear stress and shear strain, the dense sand will come to some peak strength and it will strain soften to get to the critical state. The loose sand, on the other hand, will constantly increase the stiffness and it will reach the same critical state. So, this critical state is a Cambridge construct where what we say is that if you shear anything long enough or enough shear strain is applied, all soils will reach this magic state called critical state, beyond which you cannot have any more increase in your shear stress. I can keep increasing the strain, both these lines will go horizontal. This is exactly the same as what the structures people do in plasticity. Once you've reached your plastic limit, you assume that you're not going to get any more increase in your strength, only you accumulate more deformation. It's the same concept as that. You can also look at this from volume perspective. This is the volumetric strain, and as I apply the shear strain, dense sand initially does a little bit of that and goes up, whereas the loose sand continues to contract. So, the dilation is marked positive on that axis. So, this is very straightforward, and you must have done this kind of experiment before. What about saturated soils? When you have saturated soils and you're trying to shear them quickly, rapidly, then your soil wants to undergo volume change, as we just saw. But for it to undergo volume change, the water between the pores need to move out. So, if I'm reducing my overall volume, the pressure in the pore water goes up, or the water has to flow out of the thing to keep the same pressure. If I am dense and I try to shear, the volume wants to drop, which means my pore water must go into suction, right? So, loose sands, we expect increase in pore pressure, and for dense sands, you see a drop in pore pressure. Very simple. So, when you try to do this kind of rapid shearing, the rapid shearing I am choosing because it is like an earthquake type load. You are applying 1 to 5 hertz. So, you are doing this shearing at that rate. If you do that, there is no time for the pore fluid to go out. Therefore, the pore pressure will change. Because everything in soil mechanics is linked to effective stress by the Terzaghis effective stress principle, if I change U, I will change my effective stress. If I change my effective stress, I'll change my soil strength, stiffness, the whole caboodle. So, this intergranular effective stress is the bit that allows you to carry loads, and if you are messing around with that, that will change. So, just to apply this, if my pore water pressure goes up, then my effective stress will come down, right? Because if that goes up, this is the total stress that's not changing. So, if that number goes up, this comes down, and that's what you would normally call liquefaction. In fact, you can make the pore pressure U go up so much that it will match the total stress. If U equal to P, then this becomes simply sigma dash is 0. If sigma dash is 0, your soil is no longer soil, it's a soup. So, you can't make buildings stand on soup, therefore, they will sink, rotate and fall down, right? So, that's basically what liquefaction is. If it matches fully, then it's called full liquefaction. If it's say 80% or 90% of sigma, then you would call it as partial liquefaction. Both can have its own dangers. We'll come to that later on. So, how does this reflect in the change? This is, by the way, from a centrifuge test. So, this is actually real data. So, with time, with the earthquake, the pore pressure builds up. So, at this point, my stiffness on the tau gamma plot is quite high. The slope of that loop is my shear modulus or G, right? Tau versus gamma, dt or d gamma will be my G. So, initially it's very high. So, my structure is happy sitting on the top of this stiff material. But as the pore water changes, my loop is now opened up and also rotated. My stiffness is come down. So, this is some case of say partial liquefaction. So, if I play it further, now I am almost close to liquefaction. My loop has now fallen down. I have almost no stiffness, zero stiffness, and therefore, my structure will start to sink in. And how does that feel? This is year I was born. Me and Professor Agnihotri were born, 1964 Niigata earthquake, and there was this real great Japanese engineer. This earthquake was happening at Niigata airport, and everybody were kind of running away. And this guy decided to take his 8 mm film camera and shot this. And this is a real good evidence of how liquefaction actually uh, feels in the earthquake. You can see the airplanes and how the water is gushing out, and clearly a lot of settlement because of this, and it's a real footage of liquefaction back from 1964. And as a result of that, this is a very classical picture almost everybody will show around the world, where again, beautiful structural engineering of Japanese engineers. None of the blocks had a crack in it, not even a crack, but they're all on their backside, and therefore they had to be demolished. And this is the problem with liquefaction. Typically, you would see sand boils like this. Whenever you visit earthquake affected areas, we can say which bit has liquefied, because you'll always see sand boils like this. And there are many consequences of this. For example, buildings can sink and rotate, embankments can move, and so on. Haiti was another example. I showed you some pictures before, but this is now with liquefaction. This is the main port which is supposed to deliver the relief goods after the earthquake. And as you can see, no engineer would put a crane, a gantry crane, in the middle of water in the bay, would they? I mean, this is where all the ships are supposed to come. You can have one here and one there. And the reason is this whole structure that used to support it has fallen down thanks to liquefaction. And therefore, when we showed up, it looked like this is standing in the middle of water. And here you can see there was a lot of lateral spreading. If liquefaction happens on sloping ground, it will spread. We'll come and do that properly later on in the course. But if it spreads, you can see these longitudinal cracks that are developing there. And one of those is this, and I'm standing in it. I'm not a short fellow, so it's come up to here. So the cracks are about that deep. And you can see the ground picture of that crane as well there. In our own, these are from different earthquakes. This is a shallow foundation failure in Christchurch. If you look from outside, the building looks okay. It's only a one-storied building, but you can see careful. If you compare the building to this, you can see there's a tilt. So all that has happened is the whole building has rotated, sunk a little bit and rotated. So if you are vacuuming the floor, you're always trying to go up the floor. In the end, they demolished those houses. This is the Kandla Port Harbour Masters Tower. It was supported on pile foundations, and the pile basically had punch on one side, and the whole building has rotated by about 7 or 8 degrees. It's quite visible. These are river embankments next to River Avon in New Zealand, in Christchurch, and you can see all these same kind of cracks we have seen before. With lateral spreading, you get these kind of longitudinal cracks. This is from Musini earthquake in Ecuador. One of my students went there, and that is from Bhuj earthquake, picture courtesy of IIT Kanpur. Now, if you put pile foundations, first time I'm mentioning pile foundations, so into these kind of moving ground, sloping ground, which is going for a walk, the piles don't like it, because they are standing vertical and the whole ground is gone from this side to that side. You can see the whole thing has rotated. Now, I got a frame on the top which is trying to hold these piles straight, and the piles are trying to be pushed that way. This one doesn't want to do the same. So, at the top of the pile, I'll get a hinge. Even concrete piles can form plastic hinges. As you can see, they form that by forming these kind of spalling of concrete and so on. So, I had one hinge here and one hinge here. Same thing happened in Ecuador as well. These are not big structures, but the mechanism is very clear. So based on this, we came up with this kind of two pin mechanism where you can have spreading like that and you form these hinges. Again, I will come back to this and do this properly later in the course. One of the most, it's not very old, this earthquake happened in Sulawesi in Indonesia, and this was another big issue with liquefaction. After the earthquake, this region was looking like this. Okay, you got lots of collapsed buildings. By now, we got used to seeing collapsed buildings. But what we are not used to seeing is roads getting crumpled up like this, and uh, uh, maybe in parts of Andhra, the roads are already like this, even without the earthquake, but that's just for us to worry about. But these roads were fine the day before, and they turned up like this, and buildings got collapsed on the both sides. And you won't see what caused this until you go to air. Once you start looking at aerial pictures, you start seeing this kind of damage. And this is the one I want you to take. This is stitched up satellite images by a company, and I'll play this for you, and you can see what happens. Oops, why are you not playing? So those are actually stitched up based on satellite images, and forgive the dramatic music. Uh, but before and after is quite clear to see. This is how it was looking before, that's how it looks after the earthquake. This is all because the ground liquefied and started going to walk like a river, as you have seen. So nothing makes the point better than a good visual. And similar kind of things with pile foundations we saw in Christchurch, where the moving ground, basically, whether it was steel piles, concrete piles, solid square piles, all of them were forming hinges on the top. And you can see the whole thing got rotated that way because this ground was going into the river. And I can show you many examples. In fact, there are publications in geotechnique. If you are interested, you can look at the new mechanism we were proposing based on that. Another thing that can happen is if you have tanks below ground and the soil liquefies, these tanks want to, if they're below ground, the weight of the soil is keeping them down, right? If the ground all turns into liquid, even temporarily, these want to float up, especially empty water tanks, oil tanks, and so on. And many times they do. Here is a tank that tried to pop out because all this ground liquefied. And similarly, in the Ecuador earthquake as well, we had similar examples. And if you have pipelines, they tend to float up. Along the length of the pipe, you can see it has gone up and then fallen down. That's why you are seeing this. And where you have manhole covers, in Japan particularly, they tend to pop out a good meter or so. Because the whole pipeline has come up by that during flotation. So we did some work using PIV to see the mechanism of failure for that kind of a thing. Okay, I'll come to physical modeling later on, but if you want to model this mathematically, what would you do? You basically have to solve what are called Beer's equations. So you have one equation. This is nothing but equation of motion for the solid part of the system and the fluid part of the system. So this is the overall stress tensors balanced like this. Obviously stress, mass times acceleration for the fluid, mass times acceleration for the solid, and some coupling thing. But we can separate that, and ignoring fluid acceleration, we can make it into a solid bit and a fluid bit. And if you do that, you can use finite element analysis to look at the problem. And this is what people will normally call UP formulation. U solid node displacement, P is the pressure. Don't worry too much about the maths and the equations, but that's what we are trying to do. We are going to solve the solid bit, fluid bit, overlap them together. And at every time instant, because it's a time domain thing, you need to iterate between the solid phase and the fluid phase until there's convergence, and then you time march into the next time step. But that's all maths and computational mechanics, if you like. What's most important is, to be able to do that, we need advanced constitutive models. We need to tell the computer what the soil is going to do if you apply a certain stress and strain. That is what you would call a constitutive model. If you don't know what the soil is going to do, the computer ain't going to tell you what the soil will do, because you need to give the rule, right? Otherwise, there's no this thing. And also for liquefaction problems, particularly, you're setting the computer to fail, because you're asking it to solve a problem where the system is going to near zero effective stress. If the effective stress is near zero, the stiffness is going to be very close to zero. And if the stiffness is zero, how is the computer supposed to find convergence? It will run into numerical trouble. And a lot of times this happens. And there are ways around it. I think Professor Agnihotri will talk more about it in dealing how Praxis deals with it. But liquefaction problems are really hard problems to do this particular thing. And also on top of that, you have to have boundaries, and you must have either a non-reflecting boundary or absorbing boundary as well. But the constitutive model is the big thing for us. We had a code called Swandine, which I used for many years, and we were for fun playing games with this. And here is the Kobe earthquake created this kind of gravity wall movement. It moved and settled. Somebody just did a centrifuge test on that, and I did the numerical analysis. My colleague Zheng has done that experiment, and I did the numerical analysis, and we published in AAC long time ago. It's quite well solved. You may think here I'm comparing the numerical and experiment, and if I get anything like that, we would consider that's good enough. You don't expect. So that is the experimental data. This is the numerical data. The fact that I got some point, the same excess pore pressure, makes me happy. It's not going to be better than that, because the experimental data is real soil grains doing what they want. And I'm telling the computer what my model is, and it's saying, okay, this is what I can best predict. So this is normally considered good. And as long as you got the displacements, the wall displaced by about half a meter, and if I got that right, I'm happy. So don't expect more than that. And you can do the similar kind of thing for tunnel flotation problems as well. We did numerical analysis of this. And one of the funny things is that when you shake the tunnel, it doesn't pop out because the soil liquefies. Here is the input acceleration, and here is the increase in pore pressure. But the displacement, if you plot x versus y, so the tunnel or the pipeline does that. So it's shaking horizontally while moving up, and that's why you are seeing these oscillations. While it started there, it ended up here, some movement of nearly half a meter, but it is not going in one step. It is going in stages. So to do this kind of thing, we had to go with a rectangular tunnel. This paper is, by the way, published in Indian Geotechnical Journal, and me and my son during his holidays ran this analysis, and it came out good. So we thought we should write a paper on this. And okay, we gave it a sinusoidal motion and saw what's happening to the accelerations. Those are all reducing, pore pressures increase, and the tunnel moves there. I should have an animation of this. So if I were to, so the bottom is where you are seeing where the current time is, and the pore water pressure is on the color, and the tunnel location is shown. Oops, why do you do that? So as you go through this, as the earthquake hits, the pore pressure is built up, and it's almost fully liquefied, RU of 1, and you can see the tunnel move up. As it tries to move up, the question was, of course it's going to move up. It's lighter than the soil. Why would it not move? It will move. But what stops it? Why is it not floating all the way to the surface? Surcharge is effective stress is 0, right? So there's nothing to stop it. As it tries to move up, you can see in the pour water, it has to create some suction. It's that suction that is holding it down. And this was just numerical, right? I mean, my son just graduated, so I didn't believe him, and he didn't believe me. We thought, this is what we will say. If you read the paper, that's what it says. We have no experimental evidence, but this is what computer analysis is showing. Now I have a PhD student who's actually done centrifuge tests and showed this is what happens. But this came 2 years ago. This paper was published back in 2014. So that finite element analysis is one way of doing it. Another method it's come more recently is this MPM method, material point methods simulations. There's a code called Anura 3D, and this is good for some large displacement problems. For example, if I have a slope like this and let it fail, it will go like that. This kind of works on the change of momentum equations. This is why it kind of does initially some bad things, which are not physical. But the run-out distance and the slope, final slope, seem to work okay. This is very much a new method. People don't know too much about it. So people are trying and for different problems. This is done by a colleague of mine, and now he's a professor at Texas A&M. They also try for, this is a very important problem of subsea slope failures. And there are some classical examples around Norway and Japan, where the subsea slope failures cause the soil to run for kilometers. Once they start going, they don't stop. So this is a bit like a lateral spreading, but the spreading happens over the lengths of kilometers. You can see that is nearly 2 kilometers, right? And the width is about 2 kilometers also. Let's see what the analysis predicts. This is the underwater survey revealed. This is the historic slope failure, and they created an analysis of this, and you can see, depending on the topography, that's what the computer is predicting. Clearly under predicting, but it's not too bad for something you're trying to do. Okay, I'll try and do this quickly, but tomorrow or some time I will come back and we will go through the principles of this. It's actually not that hard, but imagine I can have a small scale model of a real problem. So if I have imagine a dam of 100 meters high, in the lab I can't build a 100-meter high dam, but I can certainly build a meter high dam. So I build 1 meter high dam in the lab and put it on the centrifuge and spin it at 100 times Earth's gravity. So the soil underneath the dam will think that it is actually below the big dam. So that is basically what centrifuge modeling is. You scale down the model, increase the gravity by the same factor. Our centrifuge is this, which is about 10 meters in diameter, and it can carry 1 ton of soil up to 150 times the Earth's gravity. And I'm going to skip this because I'll come and do this properly later. What I wanted to show you is, how does actually gravity feel? The theory we will cover, he will black out for sure, right? And that's where what happens to human being at about under 10 G, it's about 8 G. We are putting our soil in the same kind of machine and taking it up to 150 times Earth's gravity. So it's not a nice place to be. Certainly I don't want to be in it. Soil has no option. We can do the same thing while the thing is spinning around. We can also shape, and this is what my specialization is. And there are some issues. We want to mimic the earthquakes in a centrifuge, but because of the scaling laws, which I'll explain tomorrow, we need to apply big forces in very short time. which means I need quite a lot of power in my actuator. And we must also be able to simulate earthquakes. So the first one I built was this SAM actuator, and this is cheap and cheerful. The whole thing costed less than 20,000 pounds to build, and we made it in-house. And it can go on the centrifuge. You can put a package on it. All it is a motor and a flywheels. I store the energy into the flywheels, and there's a fast-acting clutch which will grab onto the reciprocating rod and shake this. That's all it is. Very simple thing to do. And this was very successful. We worked for 10, 15 years and produced maybe 12, 13 PhDs for me. So it's done quite well. And it will usually produce earthquakes like this. It can only do sinusoidal motion or swept sine wave motion, and very clean earthquake at one frequency. That's what it could do. Then we thought we want to upgrade to the servo hydraulic shaker, so we started designing and building this ourselves. Actuator we had to buy and from team, and the rest of it we built ourselves. And this one has specifications of, like, it can work out 80 tons Earth's gravity, it can apply earthquake of 0.5 G, carry about 200 kilos of payload, and the most important thing is it can simulate realistic earthquake motions, not just sine waves. And it can accept all our existing containers as well. So that was our shaker, and then we put it on the centrifuge and place the table, the model container with just level bed. It's a trail experiment we were doing. And then we all get very nervous because those cylinders hold oil at about 300 bar pressure. And once the centrifuge starts rotating, they're traveling at about 200 miles an hour. So there's a lot of pressure, not just in the cylinders, but in also us. You can see it in our faces. And then you kind of hope for the best and press the button, and it does the earthquake. And here are some examples. That's the Kobe earthquake it could simulate. This is the Imperial Valley earthquake, El Centro motion, and so on. But now we can actually, most of our customers come and say, we want, especially Italians, come with their own Italian earthquake, Tolizzo earthquake or something, and say, can you fire that? I say, okay, we load the motion and it will do the motion we give it. I will talk about applications on piles tomorrow, but here is something fun I'd like to do, which is, this is commissioned by BBC. By the way, this program is available on YouTube. You can all go, and if you type in ancient apocalypses, Sodom and Gomorrah's events, you will see the whole episode. Basically, what there was a geologist from Canada who said that these two cities which are mentioned in the Old Testament disappeared because of an earthquake, and it wasn't hand of God or anything like that, because the Bible says those two people of those two cities were sinful and therefore they got punished by the God. And this guy said, no, it was a big earthquake that can happen in that part in the Dead Sea. There it caused liquefaction and these whole cities disappeared. And these were all 4,500 years ago. So they sent a geologist to get the layering of that place right. They came to us and they said, this is the layering, can you do some experiments? And I said, sure, we can do that. And this is what the model they wanted. So before the earthquake, you got rows of houses on a slope, and the slope had this silt layer on the top. So the soil here is liquefiable, but also this silt stops the excess pore pressure from disappearing. And we thought what will happen is it will flow something like this, and the water will come and submerge that. And we did that.
Images of Sodom and Gomorrah.
So this is the clip
The
from
idea
there.
is to see whether, if there's a medium strength earthquake, is it possible for these villages to actually have disappeared?
G. The model has 50 times the force of gravity pressing down on it. The houses will now react like life-size buildings. This is the point when the earthquake can be fired.
I think that's yeah, that's the, you can see the whole program later on, but basically that's how a centrifuge test works. And what we get is data from it like this, where we can measure the accelerations on the soil and also on the buildings, and what the pore pressures have done during the earthquake. And you can see the liquefaction of, you saw that rock flour that was deposited earlier that came and formed these sand boils on the surface. As I said, they always indicate liquefaction when that happens, even without the instruments. And okay, we got the pre and post pictures of the model village and so on. And we give this back to BBC. One of the things they're very good at is to create this kind of visualization based on what was given to them. So they thought this is how. Okay, so that's a good example of what happens to what lateral spreading can cause, and how some of the fun things you can do even going historically. Now, last bit I wanted to say is protecting against the sea levels. This is the kind of seawall defenses people are now constructing. This is in California, and that is a person to scale, and you can see how big these are. They're good 20-25 meters high. And the idea is you can put these K zones and reclaim the soil behind, put reclaimed soil behind it, and have a sand foundation, and hopefully they'll all work. But a better way of that takes a lot of concrete. So this Japanese company called GIAN have come up with this dual wall concept, where you have two walls that are tied at the top. And I'm going to go quickly. So you all heard of the Sendai earthquake and how the existing tsunami walls got overtopped there, and it created boats ending up on top of houses and all kinds of things. Obviously don't want the boats to be on the top of buildings, right? So that has happened as a consequence of the tsunami. And so this company, what they want to do is to put sheet pile walls on next to one another and tie them on the top. In fact, they're doing this in a place called Kochi in Japan, all along the coastline. But again, we want to see how well they work. So you could do this numerically. There are also the experimental data that has happened. And you can see that when you shake this, the soil on either side of the wall liquefied, but the soil inside hasn't liquefied. In fact, it's going into tension. Why? Because these walls are tied at the top, which means when the soil liquefies, the walls want to splay, right? If it wants to splay, the soil inside says, no, you can't. I'm here. I'm going to go into suction. And that is what holds it together. Exactly the same way as the tunnel, if it wants to float, the suction underneath is the one which is stopping it. So the link between how soil behaves and how pore water pressure is generated is critical in problems like this. That in fact tells you whether the thing is going to work or not. Okay, I'm going to stop there. I hope, although we haven't touched so much on pile foundations, at least you got an idea of why we do research in this area. It's very interesting to start with. You saw we are dealing with problems of current construction, past construction, modeling historical events, all kinds of fun stuff you can do. And that's only possible because we have the time and good students to sit down and think about things. Equipment, finite element codes, all these are secondary in my opinion. What we need is some thought that goes into the place before you start your PhDs or masters or whatever. And if you do that, then you'll enjoy it a lot more. And if you enjoy it, then the results will follow. If you start the other way around, saying, if I do this, what job will I get? The answer will always be, no matter what you do, you'll get software job. Then you don't have any interest to do what you're doing now, because I'm going to end up with the same thing. Typing C code or C++ code until AI starts writing faster than you can, then you're out of a job. So don't go that route. Enjoy the problem you're trying to do, and what is the best you can do for that particular problem. And then you'll then you need not be told. Your supervisor or a guide did not tell you to do work. You will do it yourself because the problem drives you, because you want to find a solution. We are humans, we are inquisitive. Okay, that's about it. A lot of acknowledgements, obviously, for putting a presentation like this. A lot of PhD students have worked with me, a lot of funders funded me, a lot of my colleagues helped us over the years, and so on. Okay, I'm going to stop there. The next lecture I have is on more static, and we'll now start going into pile foundations. So, what shall we do, sir? Shall we have a 5-minute break, or what time is lunch? Right. So, this is where actually I'm supposed to start with, but the morning lecture I gave just to excite you about the subject of geotechnical engineering. So, in this lecture, we kind of look at um, traditional static pile foundation design. Basically, design how do you design a pile for under static loads and also dynamic loads. Okay, and I'm going to follow what is the more recent ways of designing doing the static pile design. These are, I don't know whether these are the methods you will use in India or not, but I think Professor Agnihotri is going to go through the static pile design again. So in a way that is relevant to you directly. Okay, so just bear with me. But this is an interesting way to design piles. So let's start by looking at different types of piles. Not all piles are not the same. You can have a very soft clay and say rock underneath, in which case I can have my pile going through and ending in the rock. So if this soil is very soft, it's not going to offer me much skin friction. So more or less, all the load you apply is carried as the end bearing. Uh, on the other hand, if I have a very thick deposit of clay and there is no rock below, like in and around the coastal parts of my hometown, then you can only have a friction pile. So you have to carry the load in skin friction or sharp friction. So these both are load bearing piles. Sometimes you also use piles just to compact the soil. So you put lots of piles into the ground, and as you drive them, the sand or the soil gets squeezed in and you densify the soil. These are called compaction piles. Um, if you have a pile cap and piles like this supporting, say, a building, and you apply a lateral load, then you expect the loads, apart from the vertical load carrying, when you apply the lateral load, these piles will go into compression and tension, and therefore they need to, here you can see, this pile, if that load is applied that way, that will push down and this will pull out. So in extreme cases, you can imagine these will be they can be pulled out of the ground as it oscillates back and forth. You can also have offshore situations where they're purely designed as tension piles. So you have some floating structure, you anchor it onto the pile, and it will be effectively holding all the loading that pile will ever see in its life is in tension. Okay. Right. How do we do static design of piles? Basically, the piles are there to transfer vertical load into the soil, and even today, they are probably one of the parts of geotechnical engineering, if not the whole civil engineering, where you design them with very large factors of safety. Usually, you must be quite brave to design a pile which is less than factor of safety of 2 or 2.5 even. Why is that? Why are we so unsure about piles? I mean, if you are constructing an embankment, you can go factor of safety of 1.3, right? For other shallow foundations, maybe 1.5. When it comes to piles, generally people are very, very conservative. And you want to think, why is that? And that also means that you can save quite a lot of money if you can actually understand how these piles work and you can design better. So we'll come to that later, but basically the axial capacity of the pile has two components. So the ultimate capacity is made out of the base capacity and shaft capacity. Now how do we estimate these? So base capacity you can estimate by simply using the area times the vertical stress times some kind of a bearing capacity factor. These were done by Berzinet in 61, and where depending on angle of shearing resistance, you get the factors. So if I pick 30, it's about 30. So NQ will be 29. And you multiply that, you'll get the base capacity. What about shaft capacity? Now, the shaft capacity, you can imagine that if I can estimate the shear stress acting on the pile all the way around, and if I integrate that along the length of the pile, I should get my shaft capacity. So, you can use this type of equation where you are calculating the shear stress along the skin of the pile or the pile soil interface. You take the vertical stress, multiply that with a factor Ks, and then multiply with this friction angle. This is kind of very interesting. Why are we doing this? I don't know if you thought about this or not. So if I want the frictional resistance here, what I'm doing is at any elevation, I'm going to take the vertical stress which is acting down. I'm multiplying that with a factor Ks to turn it into a horizontal stress. So Ks is some form of earth pressure coefficient. So to convert the vertical effective stress into horizontal effective stress. That's fine. So that gives me this bit, right? Then I'm multiplying that with the friction, the coefficient, to turn it again vertical, which is my opposition to the settlement of the pile. So we start this way, convert that into horizontal stress and convert back into vertical shear stress. And once you got that for an elevation, I need to multiply that with that area there and integrate from base to the top. And that's what we are doing here. So at any elevation, you calculate K as sigma dash V tan delta CV, and then to get the shaft capacity, you basically multiply by the perimeter 2 pi r, integrate along the length of the pile. Sorry?
0.7, 0.5, how it is greater than 1.
Because you're pushing the pile in. Okay, so let's just look at some values. Yeah, delta CV, steel 20 degrees, concrete maybe 0.75 or 5 dash. There are many similar equations. I just picked a set. This is why I'm saying different countries do this differently. Wood maybe 0.66. So this is kind of material dependent, and it should be, because steel piles and concrete piles have different surface roughness. So it makes sense that these should be different. Now, the next thing is the relative density of the soil and how Ks changes based on that. So, you can have for a low relative density 0.5, high relative density 1, and if it is concrete, if it is high relative density, you can get Ks values of more than 1. That's what you're asking, right? Now, if I drive the pile in and if the soil is getting pushed out, I'm mobilizing more like passive pressure, right? So my horizontal stress goes up because my pile is being driven and pushing my soil, and a part of that will be left out as a residual stress, and that's why you can have Ks values of bigger than what you normally expect. So here what we are saying is normally Kp is about 3, and it's not quite 3 here. And in this case, where the wood can actually absorb water and swell, you can get even bigger horizontal stress.
Is it same in tension and compression, or it will be different?
No, these are all just for vertically loaded files. I'm only talking about that for now. Okay. But initiation will be the same whether it's compression or tension. Only thing it'll change is if I'm going to pull out, then the cavity will collapse and then my earth pressure will collapse. That is at the failure state. Okay, so that is like traditional design of piles. But what is getting more popular is this CPT based design of piles. So suppose I got some soil strata like this, where I got fine sand, some interbed fine sand and silt sand, fine silty sand, grey silt and so on. Typical ones. So you can do SPT or CPT, and then from that you can actually get the relative density. These are all correlations from Paul Main and other people like that. If you have one of these, you can convert them into others. How well, don't ask me, but there are cookbook recipes. It's like making jalebi. I have my SPT data, then I can convert that into stock market variations somehow. There are some correlation somewhere. How reasonable it is there some theory behind it? God knows. So let's assume that there is a recipe and they will convert the SPT blow count into relative density and friction angle. In Europe, generally, we don't like SPT so much. We prefer CPT. Offshore, always CPT. Very rarely you can do SPT anyhow. So, say I got the CPT sounding like this, where I got my QC, which is the cone resistance corrected by some method or the other, and I got this, says, solid black line as a mean. So, if I push the cone several times, I'll get many of these, and I can take a mean, and let's say that is my black line. Now, the people started thinking back in 1980s and 90s, why are we designing piles using all these arbitrary Berzhetnev method and so on if we have CPT data? What is CPT? CPT is just a rod, narrow rod, which you are pushing into the ground. And we are monitoring what's going on at the pile tip resistance, cone tip resistance, and also shaft sleeve resistance and other pore pressures and so on. So we actually got, the soil is trying to tell us, if you push an object into me, this is what I'm going to do. So why don't we use that to design a pile which is nothing but an enlarged version of the cone? So there should be a really nice correlation between CPT and SPT. That is the theory behind these methods. And these are getting quite popular. So, if I have, so this is a typical CPT truck. I believe Aniruddhan or somebody in Chennai has a truck like this. And there are a few others who can buy them, and clearly there are not enough of them. That's why we are still struggling with SPTs. But you use the truck as your reaction and you push the rod in between. So you can see your the whole weight of the truck is your reaction load, and you push the rod inside and you get your QC values directly from that. So if my pile was to be a board pile, that is, if I'm going to make a hole in the ground, drop the reinforcement and pour concrete, then I can link my QC that I get from my CPT to the pressure I'm going to get or the resistance I'm going to get for the pile, end bearing of the pile. So QB over QC is a ratio that's approximately equal to the displacement I'm going to get at the base of the pile normalized with the pile diameter, same here, plus 0.5 QC over EB. EB is the Young's modulus of the material. If it is a concrete, then you use the Young's modulus of the concrete there. So this is like a nice correlated link to the CPT. So if I have QC, I can basically get what QB is based on that for different diameter piles. If it was a driven pile, same idea, but now it will, you use this equation And obviously, this will be a lot bigger than for board piles. Board piles at the start of their life has very small vertical stiffness because they need to displace some amount to mobilize the full base capacity and shaft capacity. Whereas a driven pile, you already driven it to the soil underneath should have failed for it to arrive there. So you will start with much higher capacity. And you use this equation where again this is the normalized displacement at the pile base to diameter plus the half of that, and yeah, the only difference is the in the top you have this QB naught, which is the residual pressure. At the bottom you have QC, which is the cone resistance at different elevations. So we can get a continuous variation of the shaft of the bearing capacity with depth using this equation. Typically, you don't actually measure that. You take the ratio of the residual pressure to cone resistance as about 0.3 to 0.7 seem to fit reasonably well. So that is one way of doing it. There were these people, Richard Jardine and Fiona Chow, came up with a slightly better and elegant way of doing the same thing, and in fact, it's much easier to use. So this ratio of QB and QC, now what they are linked to is this equation where D is the pile diameter and D cone is the cone diameter. So I only need two. The diameter of the pile I want normalized by the diameter of the cone, which is normally maybe an inch and a half thick rod. That's the cone rod, right? And this is a natural logarithm or Lund function, we call it. And this would be greater than or equal to 0.13 is the equation. So if you plot this for different pile diameters between 0 to 1.5, you can see this will tend to about 0.13, as I said. If it is any lower than 0.13, you make it 0.13. But say for a half a meter diameter pile, I would get QB or QC of something like 0.38 or 35. Easy. So I only need to know QC, then I can work out my base capacity. And here what they're assuming is internally that as I'm pushing my pile or the cone in, the soil around is undergoing cavity expansion, and that expansion ratio is like a Lund function or a logarithmic function. Randolph later on has come up with, that is the earliest one. Then they also modified this to came up with this for driven piles to work out tau s as well. So the previous one gives base capacity, easy. This one gives you the skin friction or the shear stress along the skin, and so here you have QC over 45 and the vertical stress normalized to atmospheric pressure to 0.13 d over h to the point. I never like these kind of these basically means somebody fitted a curve. That's what these 0.13 and 0.38 are. This is the residual thing. That whole thing multiplied by tan delta CV. Tan delta CV makes sense because that's just your mu or the quotient of friction. So that is all fine. This delta sigma dash RD is the stress increase due to dilation. You asked earlier how come I can get my K greater than 1. This is the one that is creating. So as I am pushing the pile in or driving the pile in, the soil is expanding radially. That makes the soil to dilate. And this basically is trying to work out that stress increase due to the dilation. Okay, so that they add here and work out tau s, and then as before, once you got tau s at one depth, you integrate along the length of the pile to get the tau s. Shears. Mark Randolph actually modified this, and this is in his Rankine lecture in when did he do? 2005 or 6. It's based on his previous paper, and this tau s, what Mark says is it's not a Lund function, logarithmic function for the expansion. it should be a negative exponential function. So in a log function decays quite slowly, an exponential function decays much faster. So he, based on his experience, said, as I move away from the face of the pile, my cavity expansion pressure or the stress will decay much faster than the logarithmic function will give you. That's all the difference. It's just maths. So how do we estimate this based on this exponential function? So you take the minimum earth pressure plus difference between maximum earth pressure minus minimum earth pressure. So basically Kp minus Ka, if you like, times e to the power of minus mu h over d, where d is the pile diameter, mu is the coefficient of friction, and the rest are all known. So effectively, we can recalculate tau based on this equation, which is much more reliable, and he has a lot of data to show this actually works better than the other one. So you can actually take this Kmax is taken proportional to the cone resistance QC. Basically, you need to know how much of your passive earth pressure are you mobilizing. And what he is saying is you can take that about 1 to 2% of QC over sigma dash V. All these are in the paper. So this is not what I wanted to, as I said, you should not worry too much about the equations. It's basically you need to know why, what is the basis behind it. So this one is saying there's an exponential decrease of my horizontal stress as I move away from my pile soil interface, whereas the previous one is saying there's a logarithmic decrease. Okay, so that's all. What that we have covered so far should let you design a pile for a given load easily, whether it's board pile or friction or driven pile. That's how I would, in a typical Cambridge style, we say, yeah, we covered pile foundation design. Go away and do it. Now, obviously, here you have many more. I'm sure there are IS codes. I don't know, IS 18, 15, yeah, so there are IS codes which you have to follow, and they'll follow one method or the other. For us, it is more important that you understand where these equations are coming from. That's why I chosen the latest one from Randolph's Rankin lecture and showed you how you can use that in design. Now, IS code may or may not allow that, but then it's IS code's problem, not my problem. Okay. Right. Now I want to, we want to actually move away from that and look at the dynamic design of considerations for piles. So all we have done so far is static. First thing about piles and dynamic loads is there are two types of loads a pile will attract. One is called inertial loading and the other one is called kinematic loading. So what I'm going to do is to explain what these are, how we have methods to evaluate it at the moment, and also I'll show you whether they're any good or not. So again, the idea is there are equations, there are ways to calculate, but then you need to go and check whether what you're doing is right or not. And that's where research is important. We are not doing this for fun. Okay. First thing is inertial loading. What is it? I got piles supporting my building. The earthquake comes, it shakes the ground, the piles, and the building. Now, the building has quite a lot of mass sitting on the top, right? So, if I try to accelerate it, that is going to apply big loads onto my top of the pile. Yeah? So, for now, let us call that is the inertial load. So, the piles are the ones which are holding the building and trying to move back and forth, and the building says, no, I don't want to go, I'm heavy. So, that is why it's called inertia. It doesn't want to move. The piles want to go, the building doesn't want to go. Therefore, the building applies to the piles at the top this inertial load. So, the first thing is, if you don't design properly, all the pile heads will break and the building will break free. That's one possibility. The other one is kinematic loading. So, kinematic loading is the piles are buried in the soil and the soil is wanting to go left and right during shaking. So it wants to take the pile to ride with it, right? But pile has its own stiffness, soil has different stiffness to the pile. Pile is made out of concrete, soil is made out of soil. So clearly they don't have the same stiffness. So because of this difference in stiffness, the pile will move less and the soil will move a lot more, because soil is typically softer than concrete pile. So if the soil wants to move a lot more than the pile, it has to go past the pile, right? So as it tries to go past the pile, it says, oh, you are stiff and I want to go past you, so I will mobilize my passive pressure. The biggest problem with soil is whenever it wants to go and somebody is trying to stop it, it will mobilize a passive pressure, which is a lot bigger than a normal, say, earth pressure at rest. So because of that, the pile will see extra loading, and that is what we call kinematic loading. So it's that the clue is in the name. Kinematic loading is coming because something wants to move and somebody is stopping it. Inertial loading is coming because someone wants to move and the other fellow doesn't want to move. The building doesn't want to go, the piles want to go. Therefore, that is called inertial loading as defined by Newton all those years ago. Now, we have seen umpteen examples of these piles failing. Again, this is why it's important to go and look at these things that have fallen over. This is from Taiwan 921 Chichi earthquake, where you got this bridge, not big bridge, it's a fairly minor bridge with piers, and the whole of the pier rotated, making the decks fall off. You can see the decks have fallen off the pier. Why is that? This is because the decks are very heavy, and when the earthquake came, the decks wanted to slide back and forth, and in doing so, they pushed the pier and they broke the piles at the bottom, at the top of their head. Then the pier could rotate, which means that there is enough space for the deck to fall down. That's what has happened. So this is a case where inertial loading from the superstructure, the decks and the pier, applied large lateral loads on the top of the pile, failing the pile and therefore causing the failure. The other case is the kinematic loading. Again, same earthquake, different bridge. Here, as I said in the previous lecture, if I have sloping ground and the sloping ground liquefies, it will go for spreading, right? So it will spread down, and these are the longitudinal cracks I showed you in the previous lecture. So this is all because the soil wants to go towards the river, down slope. It doesn't particularly like when we put big bridge piers and piles in its way. So what we have done here is we've created a large bridge pier in that slope, and the soil wanted to go down slope. You can see this, it moved away from here. This used to be here. It moved about 3/4 of a meter. And that is a bigger close-up of that. That is not a problem. Soil leaving the pier and walking down the slope is not a big issue for us. But equally, same amount of soil wanted to come from the top, right? Now, this pier is the one who's stopping the soil from coming. As I said, if the soil wants to leave the pier and go away, it will go with nice active pressure, which is less than earth pressure at rest. Ka is less than K0, right? So that is not going to cause us any problem. But the one that is coming is going to come with Kp, which is 9 times larger than the active earth pressure, roughly. If you take phi as 30 degrees, it's 9 times bigger. So the horizontal loads that your pier is going to see because of this will be huge. Even if I had 2 meters of soil, 2 times say 15 to keep the numbers simple, 15 kPa is 30 kPa. That's my vertical stress. Multiply that with a factor of 9. That is how much horizontal stress I'm going to get. And you integrate that over the area of the pier, the load will be significant. And that is all actually kinematic load coming onto the piers and the piles below because the soil wanted to go walking and you stopped it. It doesn't like that at all. So this is all coming because of the movement of the soil. Therefore, we should call it the kinematic loading. Right. I'm not the first one to talk about inertial and kinematic loading. This has been going on for some time. And let's see where we are. Now, typically, say I got a pile cap and say that is the column of the building and the cross beam or the ground beam. So this will sit on these normally. But what I want to say is that the structure will have its own acceleration, say going from right to left. Then the inertial load will come the other way, and that will be the direction in which the load is applied onto my pile cap. Just the free body diagram of that. If you do that, if the pile cap rotation is allowed, in other words, this can rotate like that, i.e. this connection is not rigid. So the column is there, but my pile cap can rotate. That means I'll form 2 hinges here. If my pile cap is not allowed to rotate because that is connected solidly to my pile cap, then it can't obviously rotate. So it will go translating and therefore it will bend like that. If I got a lot of depth here, I can accommodate that much movement without forming plastic hinges. But if these are shorter or smaller layers, then I will form plastic hinges. Okay? So that is clearly where I am trying to stop or have a particular type of failure in my piles depending on what the structure is doing. This so far we haven't got the soil involved at all. The pile cap is there, the piles are there, but depending on how the structure is connected to the pile cap, we can get different types of failure mechanisms. So this is one example of this soil structure interaction. We need to know what the structure is doing. Is that a framed building? Are there cross beams joining? All that detail we need to know before we can determine what the type of failure is. Now, because the buildings are quite heavy normally, your inertial loads are always going to be very big. What is kinematic load? In the other way to create kinematic load, suppose I got an earthquake, stiff clay, soft clay, my piles are going through the soft clay and into the stiff clay, and because of the shaking, let's say I got the displacement profile, it used to be vertical, I formed this kind of shape. So the piles want to do this and the soil wants to do this, and because these two displacements are not matching, I will get the kinematic load coming onto my piles. Again, the kinematic load may be more on the front pile compared to the back pile and all kinds of funny things. It also depends on the pile spacing, and there's a lot of research we have done and other people have done to see what is the load difference between front pile and the back pile, and so on. Again, if the pile cap rotation is not allowed, you will get a totally different failure mechanism. Another point is, this is quite important, is will the inertial load and the kinematic load will happen at the same time or not? And this is what we mean by phasing. So it is possible that the earthquake comes and it shakes. So at that time, I have my inertial loading. But the earthquake shaking causes the soil to go walking down the slope. That will happen maybe after the earthquake is finished or between at least some time after the earthquake has started, right? So the kinematic load and the inertial load may not be in phase. They may be out of phase. So you should not again simply take peak inertial load, peak kinematic load, and add them together, that is probably too conservative because they may not happen at the same time. But if you want to be conservative, you can do just that. Right. The other thing is, how do you know whether the piles are rigid or flexible? So this is one way the Eurocode kind of tries to do this. I'm not a fan of this, but I can't only teach things I like. When other people have done some things, even if I don't like, I have to at least mention them. So what they have done is, you need to know what is the active length of the pile. That's what LAD is. In other words, for example, in this case, although I have pile all the way going down, this bit of the piles are probably just straight. So they are not doing anything. So I only need to know this length of active length of the pile, which is undergoing bending. And this is a way of calculating that. So what they say is you can calculate this by 2 times the diameter of the pile, ratio of the Young's modulus of pile to Young's modulus of soil at one diameter depth, one pile diameter depth, to the power of 0.22. Again, it's a fitting exercise. That's why they come up with that kind of stupid numbers. But more importantly, before I get too upset about 0.22, I got more upset with this EST. What is it? I've been in soil mechanics for nearly 40 years now. What is Young's modulus of soil? This is not steel, this is not concrete. Our soil doesn't have Young's modulus, let alone measure Young's modulus at one pile below ground. One pile diameter, say it's half a meter diameter pile, you're looking for vertical stress half a meter below ground, which is tiny, and you're trying to say, oh, I want to know the Young's modulus. There is no such thing. So this is a stupid thing that numerical people have. In computer code, you can enter a number, and okay, we put Young's modulus for soil, for steel, Young's modulus, Poisson's ratio for steel, concrete, likewise. Why can't you guys do the same for soil? And that's because our soil doesn't behave that way. But anyhow, this is what is in Eurocode, and that's what it is. Then pile flexibility they calculate as, say, some factor T. Again, Young's modulus of pile, fine. So EI of the pile, and here K is the subgrade reaction. Again, this is like measuring the spring stiffness of soil, and this, and you can see why this is stupid, right? K can have values from 200 to 2000. Really? That is a factor of 10 on design? Yes, we can put the numbers, we can do, if it is an exam question, students, you give the number, they'll put the number, do the it's just an calculator exercise. It doesn't mean you're doing any design. Anyhow, so if it is loose soil, they immediately plug the higher end of that number, 2000. Don't ask me why. Similarly, for inertial loading also, you can work out the elastic length Z max based on L over T. So I already got my factor T from here, and I know the length of the pile. So Z max is the active length of the pile, or LAD. Okay. So if it is greater than 5, the pile is flexible. If it is less than 2.5, the pile is rigid, and in between it is semi-flexible. Similarly, methods are also there in Brom's and other textbooks, where you can see whether the pile is flexible or rigid. But this is for more dynamic loads. So what about inertial loads? So that bit we looked at pile movement and soil movement and where the length of the active length of the pile. But when it comes to inertial loading, it is again we need to determine whether the pile is flexible or not. If it is flexible, it will move with the surrounding soil, and therefore it will attract that inertial shear load at the top of the pile head, but the kinematic loading will be small because the pile is already moving with the soil. There is no, it will deform the same way as the soil does. So the amount of kinematic loading will be small, but you pay the price in inertial loading. Rigid piles, on the other hand, will stay there where they are. So hopefully you will get less amount of inertial loading, but more amount of kinematic loading. So how do we work these out? So you work out the kinematic interaction factor is defined as this IU. Basically, what is the pile displacement any depth divided by what is the soil displacement. So we are dividing the pile displacement with soil displacement to get my interaction factor, IU. And then we can also work out this dimensionless factor F, which is, here is the first bit of taste of dynamics coming in. F over Fn is the frequency ratio. So F is the earthquake predominant frequency. Fn is the natural frequency of my pile soil system. So that is the dynamic bit. This is the stiffness bit, EP over ESD, pile Young's modulus over soil Young's modulus to the power of 0.3, and L over D is just a geometric factor, length of the pile over diameter with minus 0.5. So if I have this F, I can link that to this IU through these, and basically Eurocode gives these ABC values for clearly a fourth order polynomial somebody fitted to this. Okay, and depending on how the soil stiffness is changing with depth, if it is constant, you have these values. If they are parabolically changing with depth or linearly changing, these ABC factors change. So you plug these into there, work out the IU for kinematic interaction. Okay, now this is all great. So we got a recipe for working out kinematic interaction factors and inertial interaction factors, right? Are they any good? Mostly I'm focusing on inertia, kinematic interaction, because inertial interaction, I can always take the mass of the building, multiply that with the earthquake coefficient, and I can get the, sorry, it's auto playing. Multiply with the PGA, I should get the total possible inertial load. It can't be worse than that. And I can divide by number of piles, I'll always get that quite easy. Kinematic interaction is more important because that depends on what the soil is doing as well. So this is the work Tejesh has done. Garala is a new assistant professor at IIT Madras, and when he started, came to look at soft soils, piles in soft soils. So all kinds of soft soils can amplify the seismic motion, and they're influenced by amplitude, frequency, and duration of the ground motion. That's what we want to look at. And there are plenty of examples where soft soils caused trouble in the past. This is the Mexico City 1985 earthquake, where the earthquake was fairly small away on the hills, but at these locations it has magnified from 0.05 G to almost 0.2 G, and that caused all these buildings to fail, and buildings of certain height to fail. Very tall buildings were fine, very short buildings were fine. The buildings which were 20 stories to 25 stories all collapsed. And this was a very interesting problem to look at that time. And people did work like, how the depth of the clay layer increased from here to here. It goes deeper and deeper because Mexico City is on a clay bed, a dried out clay bed, so the clay is very soft. It's a very famous geotechnical case. So what we did was, we had piles which are short in soft clay. So his system was soft clay dense sand. So we had single pile group of 3x1 pile group, all stopping in clay. And he also had in another experiments, the piles went into the sand. So we'll start with the clay ones first. And that came so this is the experiment. Again, I'll do the centrifuge modeling part tomorrow. I can't do everything at the same time. But you can see he created a soft clay and he installed these piles, and it's all, everything is in clay. So these are what you would call floating piles. So piles which are not actually going into the sand. And he tried different earthquakes. I'm not going to go into all the detail, but we can also push this like CPT. We can also do a T-bar. So while the centrifuge is spinning, we can push this T-bar, which basically gives us the, like QC, you can get the, it's linked to underhand shear strength. So we can measure underhand shear strength with depth while the thing is going on, before the earthquake, after the earthquake, and so on. And we can also measure shear wave velocity using another device called air hammer. You shake this air hammer very gently and pick up the upward propagating waves, and you measure the shear wave velocity based on wave arrival times. So this is all done, and again there's a paper if you want to look at that. But the interesting thing was that we could see how the accelerations as they go through the clay change. So there are some components which get bigger and some components which get smaller. By the way, this work was done with the SAM actuator, so we didn't have the servo hydraulic actuator right then. He used it later on. And what we could see is that for bigger earthquakes, these high frequency components are disappearing. So clay is acting as a nice filter to get rid of high frequency components which are there at the bottom but not at the top of the clay. Also, we could work out the, using this G over G naught curves where our data falls and fit a line through that and work out at any depth what the shear stress is. It's just a bit of maths, don't worry too much. But what we worked out is, if I look at a certain depth like this, beyond, above here, my clay is not strong enough to carry the applied earthquake. So I'm applying here an earthquake that is nearly 0.25 G. Okay, very strong shaking. So if I apply very strong shaking, clay does not carry this above, because its shear strength is only that there. If I exceed the shear stress, it is not going to carry that above that elevation. Okay, so it basically, it fails nicely there and protects your structure on the top. So we want to kind of use this to make holes in deep soil. Deep soil is a computer code which people use routinely to do site characterization. So if you put the same, so if I put small earthquake, everything goes through. Big earthquake, our experiment is showing the accelerations all fall off, right? But if you do the deep soil analysis, which doesn't have a failure criteria built into it, it will predict, because the soil is like a clay, a soft sponge. If you shake it strongly, it says it wobbles a lot. And so you need to have some yield criteria in the program, otherwise it will predict. So the blue line is what the computer prediction is, and black line is the reality. So you should not use computer codes without knowing what they are doing. And the pile response also, you can see, if I apply the big earthquake, although the clay doesn't respond, the top of the piles actually oscillate a lot. That's because I use the pile to connect the stiff part of the clay to the top. So the rest of the clay gets protection because it gets isolated, but the pile itself will carry the load and oscillate quite strongly. Okay, that's all fine. The other part we did was to put these piles into sand. This is the most common case. Floating piles are very rare, to be honest. So that was just fun and to tease the guy who wrote Deep Soil, who I know, Hush Hush. Yosef Hush Hush was the guy's name. Anyhow, So we put single pile and multiple group piles into this profile. Come on, yeah. And again, we can measure the strength with depth, under and shear strength using the T-bar. We also do the shear modulus, and you can see this is where the jump in stiffness happens, because this is all sand, that is all clay. This one is only being plotted up to here. Okay, this 6 meters or 7 meters ends here. We can't use our T-bar to be pushed into sand, otherwise it will break. Sand stiffness is 100 times bigger than clay. So you can either design the device to work in clay or sand. You can't do both. So that's why you haven't got CU profile in sand, which doesn't make any sense. Anyhow, we got the natural frequency of this, and most importantly, we measured the bending moment of in the pile for different earthquakes, right? We got, these are the points where we are measuring the bending moments, and now we've done that, we could compare the minimum and maximum bending moment envelopes. And luckily for us, in literature, there are quite famous people who put their name and gave estimations of how to calculate kinematic loads on piles. For example, Dobry and Ricardo Dobry, Tomoror, Nicolau, Milenakis, lots of big names. And all Tejesh has done is to collect all their equations, and he worked out these values according to what they said, and he plotted the maximum bending moment that we should get based on their calculations. So for small earthquake, blue line is our experimental one. Those equations always give you the number at only one depth. You can't do them for different depths. So he chose this 9 meters is where they calculated. So we also did the same. And this is where the experimental values are. This is value is, and these are all the predictions by different researchers. So great, no problem. That is not too bad. I mean, for small earthquakes, it works fine. But when we increase the size of the earthquake, the peak bending moment for us goes up to about 450 kilonewton meters for this sized pile, and all the theoretical predictions fall here. So, oh, that is not good. That means all these equations that are there can only work for small earthquakes. If the earthquake size is big, we are in big trouble, because we are getting a factor of 2, 2.5 above what they're estimating. And as I said, our factor of safety for pile design is about 2 and 2.5. So all of them will fail. So we wrote a paper to compare the bending moments with the theoretical predictions. Our centrifuge data is showing all these black dots, and you can see all the theoretical ones are tailing off here. So we are getting, for bigger earthquakes, we are seriously underestimating what the peak kinematic bending moment is in the piles. So what have we learned? So we have learned that pile foundations have this type of loading called kinematic and inertial loading. Those are separate. And there are ways, theoretical, semi-empirical, some made up methods for estimating the inertial and kinematic interactions between the pile and the soil. We've seen those. But more importantly, we learned that if you design the experiments, you can get at least validation or otherwise of how good these solutions are. And I hope I have shown you that if just by considering bending moments, nothing else, we could show that the existing methods work reasonably well for small earthquakes, but fail miserably when it comes to large earthquakes. So the process of learning was, there is this problem of pile foundations. There is static load, dynamic load. There is ways of calculating them, but more importantly, we must have ways of telling the calculation procedures are right, overestimate, underestimate, is it safe or not. Okay, so I'm going to stop there. Any questions? No need to. If you clap every time, we'll be clapping. You can clap at the end of the course, okay? Yeah, yeah.
Normally in M-bearing estimation there is CPT, there is an averaging of 2 to 9 meters up and down.
Yeah, yeah.
Why it was not?
You could do. I mean, here you can see because it's coming at the. This is coming quite low. So whether you average it up and down, it's not going to make difference. I'm not. There are many variations of applying the CPT. I'm not arguing one is right or not. Also, the CPT at very shallow depth, the failure mechanism doesn't fully form. Therefore, it is also there. I think Dave White or somebody came. There's a paper saying how do you correct for shallow layer correction for CPT and T-bar values, especially for soft clays, offshore Perth, right? Yes, you can do that. I'm just trying to teach that try to use CPT direct correlation. I like that because you're doing exactly the same thing to the soil, whether you're driving in a pile or a CPT. So surely we should be able to scale from CPT to pile much better than trying to work these bearing capacity factors randomly. For offshore, you certainly should use CPT, no question.
Or again, another question is related to this. Since we are pushing CPT T precedent itself is an average value.
It is what it is, right? It's what soil is doing.
It's a like average value. And again, why we are doing this averaging?
Oh, that is because of the layer. Yeah, CPT is a funny thing, right? We have some very interesting experimental results. When do you think the soil will feel the arrival? Say I'm driving the CPT here and I'm the soil here. When do you think I'll see that CPT is coming? Can you guess? So the CPT can be felt by the soil element maybe 3-4 pile diameters ahead. So when the CPT is here, I can already feel the increase in stress. Then it goes increasing until it goes past the location, and then once I go past, you can see that it starts to relax. So you can pick this up using the pore pressure transducers around, and there are very beautifully done experiments. I think Delft or even Nantes has some tests like that to show the arrival of the CPT. So yeah, that is why they try to average the along. That is to account for the length direction along the driving direction. This what you are saying is along the lateral direction. So you need both. It's but the good thing is if it is doing that for the CPT, it will do the same when you drive the pile. That is the assumption, right? It's just a scaled up version of that. Any other question? Professor, you want to ask something? No? Okay. Right. In that case,
Induced settlements. If we see past history, soil liquefaction has been major cause of damage to soil structures, lifeline structures, building foundations during past earthquakes. He has already shown you some pictures, so I have not included those pictures again, and clearly poses significant threat to the integrity of structures and other facilities during future earthquakes. Evidence of occurrence of liquefaction has been reported from large number of earthquakes. Shonai 1894, Assam, Kanto, Bihar, Pukoi, then Assam 1950, Jaltipan, Chile. But it was only after earthquake at Niigata and Alaska in 1964 that the problem of soil liquefaction was investigated in greater detail, and efforts have been increasingly directed towards the development of methods of evaluating the liquefaction potential of soil deposits. Only after 1964 earthquake, people started working towards liquefaction, detection of liquefaction, why liquefaction takes place and how to measure it. Soil liquefaction, as already explained, that describes the behavior of soil that when loaded suddenly suffer a transition from a solid state to a liquefied state, or having the consistency of heavy liquid. Liquefaction is more likely to occur in loose to moderately saturated granular soils with poor drainage, such as silty sands or sands and gravels capped or containing seams of impermeable sediments. If we see this picture, you can see boundaries, these boundaries. If soil is between these boundaries, that is most liquefiable soil. If it is within this, it is most liquefiable. This is also liquefiable. If it is beyond that, if your soil is not in that part, beyond that these boundaries, then there are minimum chances, no chances you can say of liquefaction. Now, evaluation of liquefaction potential. First, based on SPT, standard penetration test. All of you must be aware of standard penetration test. We calculate N value. We give number of blows of 65 kg hammer and penetration for 300 mm penetration through a free fall of 75 centimeters or 750 mm. Number of blows are counted for 300 mm penetration, that is N value. So N value is recorded. Here it is written N160. N160 because there is energy loss when hammer energy is given, some energy loss is there, approximately 60% energy remains that is actually applied. So that's why they have named N160. So actually N160 is observed N value. So N160 is then Nm is observed value actually. Nm is observed value. Then we apply some corrections to that, we get N160. N160 is corrected N value. So N160 is Nm into Cn, Ce, Cb, Cr, Cs. These are correction factors for overburden resistance, correction factor for hammer energy, correction factor for borehole diameter, correction factor for rod length, correction factor for samplers with or without liner. Because overburden changes as we go down, overburden changes. As we go down, more overburden is there. So we rationalize the values, because where overburden is more, there you will get more confinement and higher N value. So we reduce those values to some extent. Okay. So different corrections. This I already told you that why 60% we take, because actual energy transferred is 60%. Then correction factor for overburden pressure. For overburden correction factor, we multiply with Cn. Cn is Pa upon sigma V0 dash raised to power 0.5. Pa with 100 kPa we take, 100 kPa, and sigma V0 dash effective overburden pressure at the depth of SPT. Suppose SPT is conducted at 5 meters, then within that 5 meters, considering the water table, we convert gamma to gamma submerged wherever required. So that's why effective, not total. Effective overburden pressure at the level at which test was conducted. For other corrections, this table is used. We will borehole diameter correction. If diameter is 65 to 115, then then correction factor is 1. For 150 it is 1.05, for 200 mm it is 1.15. Similarly, energy ratio for safety hammer, for donut hammer, which hammer is used. Accordingly, for different types of hammers, these correction factors are applied. For rod length, if rod length is 3 to 4 meters, test is conducted within 4 meters, then for those values correction will be 0.75. Then for values of SPT N values which are between 4 to 6, correction factor is 0.85. Like this, these correction factors will be applied. Similarly, sampling method. Now then, this N160 which you have calculated, then it is converted to N160 for clean sand. In our soil, fines may be more than 5%. If fines are more than 5%, then it is not clean sand. If fines are less than 5%, then we consider it clean sand. We convert our value to clean sand value, because curves which are available, which are reliable, considered reliable, they are for clean sand. So we convert our N160 value to N160 CS. This N160 CS for clean sand. So alpha plus beta N160. Alpha is calculated, this coefficient is calculated as exponential 1.76 minus 190 upon FC square. Similarly, beta 0.99 plus FC raised to power 1.5 over 1000. This FC is fines content in percentage. This is in percentage. If fines in our soil, they are say 35%, then FC will be 35, not 0.35 in this equation. So, then 30 FC will be in percentage. We will calculate alpha and beta, then substitute the values of alpha and beta in the equation. You will get N160 CS. So, N160 CS you will calculate. Then curves are available. Those curves I will show you first. These curves are available. From these curves, this curve is for fines content less than equal to 5%. Less than equal to 5% means clean sand. So we will see this curve. This is cyclic stress ratio, and here we have N160. On these curves it is written N160. We will see this curve. So whatever value you have calculated N160 CS corresponding to that value, N160 CS value corresponding to N160 CS value, we see this curve, whatever value you will get, that is cyclic stress ratio. This is cyclic, actually this is cyclic resistance ratio. Cyclic resistance ratio. Though it is mentioned on this curve, this CSR, this is CRR. Okay? You will consider it resistance. And secondly, these values are for earthquake of magnitude 7.5. This is for earthquakes of magnitude 7.5. If you are expecting earthquake of different magnitude, then correction is applied. Magnitude scaling factor, that I will let you know. This magnitude scaling factor, CSR M over CSR M equal to 7.5. That ratio is magnitude scaling factor. So magnitude scaling factors are there. Suppose you have considered earthquake in that particular area for which you are going to calculate liquefaction potential. If expected earthquake is say of magnitude 7.5, then that magnitude scaling factor is 1. If expected earthquake is a 8.5, then magnitude scaling factor is 0.89. Similarly for others. So accordingly you will modify the value of CRR. Okay. Now other value, cyclic stress ratio. That was cyclic resistance ratio, which you have calculated from the curves. Now you will calculate cyclic stress ratio. Cyclic stress ratio is calculated using this equation 0.65 sigma V0 A max upon sigma V0 dash into RD. RD is stress reduction coefficient. Stress reduction coefficient that accounts for this is stress reduction coefficient that accounts for the flexibility of soil column. For example, RD equal to 1 corresponds to rigid body behavior. So that depends upon flexibility. So sigma V0 and sigma V0 dash. What is sigma V0? Overburden pressure, total, and sigma V0 dash is effective. So if you have conducted the test at say 6 meters, then water table is, let us suppose, at 4 meters. So up to 4 meters, gamma into 4, if soil is same. Then beyond 4 meters, it will be gamma submerged into 2 meters. So like that you will calculate this sigma V0 dash, and this sigma V0 is total. Here we will not consider that effect of submergence, we will always take total. If above the water table, it is total. If below the water table, then gamma saturated. Total is gamma saturated below the water. So 0.65 sigma V0 A max acceleration, expected acceleration in that particular area. Let us say earthquake of 0.25 g is expected. If earthquake of acceleration 0.35 g is expected, so this A max will be 0.25 or 0.35 or 0.3, like that. So sigma V0 you can calculate. You have performed SPT. After performing SPT, you will get N1 and you will get Nm, measured values. Then convert to N160. Then N160 will be converted to N160 CS. Then you can see the curves. From the curve, you can calculate CRR. Now you have to calculate CSR, stress. For that, sigma V0 you will calculate at the same level at which SPT was conducted. At that level, sigma V0 and sigma V0 dash will be calculated. A max expected earthquake acceleration 0.35 or 0.3 g or 0.25 g, like that. So we will take in terms of g. G we will not write in this equation. A max, if earthquake is 0.3 g, we will take A max equal to 0.3. Okay. Then RD, stress reduction factor. Stress reduction factor we can take from these equations. Stress reduction factor we can calculate if Z is less than equal to 9.15, then this equation. If it is between 9.15 to 23, then this is the equation, and so on. Like this we will calculate RD. Now everything we have in that equation. So from that you will calculate CSR. Now you have both CRR and CSR. RD you can calculate from curves also. That table is also given after conversion. Now we will compare CRR and CSR. If your resistance ratio is higher, if resistance is more, naturally factor of safety is more than 1. So if factor of safety is more than 1, then earthquake is, liquefaction is not expected. If ratio is less than 1, then liquefaction is expected. So you will calculate factor of safety, CRR upon CSR. I think clear? For example, let us suppose we have N value of 12 and gamma value is given to you. Water table is also given somewhere at 3 meters. We are earthquake of 6.75 magnitude is expected. We are to maximum ground acceleration is expected in that area 0.35. Calculate factor of safety against liquefaction. So we will calculate sigma V0 dash. Here we have taken minus gamma W submerged below the water table. So 21 minus 10 we have done. Gamma saturated minus gamma W. So let us say this is 76.5. Now sigma V0 total average earth pressure. So 20 into 3, this will be 21 into 1.5. Total we will take, so it's in 91. Now similarly, stress reduction factor from this equation, we will calculate that is, let us say 0.965. CSR 0.263 from the equation we can calculate. Equation which I have shown, from that you can now calculate CSR. Now next is CRR. For CRR N160, NM is given to you 12, that is given in the problem, and NM 12, then these correction factors will be applied. After applying the correction factor N160 13.8, now we will convert this N160 to N160 CS. N160 CS for fine contents say 15%, so N160 CS is 17. So we have converted this N160 to N160 CS. Now from the curves which I have shown, from this curve now, because we have converted to clean sand, so corresponding to 17, approximate value is 0.185 from this curve. So that value, so 0.185 is CRR. Now magnitude scaling factor, because this CRR is for an earthquake of magnitude 7.5. In our problem it is given 6.75. So from the table we will see magnitude scaling factor and divide, this ratio will be multiplied by magnitude scaling factor. So answer is 0.92. This is less than 1. Therefore liquefaction is expected to occur. So this is how we calculate the liquefaction potential. Wherever we go for soil investigations, normally we find out bearing capacity. We conduct the test, then we calculate bearing capacity based on shear failure, then calculate bearing capacity based on settlement. That's all. But at the same time, liquefaction potential should also be seen, whether liquefaction is expected in that area or not. Same N values we can use for this purpose also. Then cone penetration test. Based on SPT, we can have that. Similarly, if cone penetration test is performed, when you perform cone penetration test, in the first stage only cone is penetrated. Second stage, cone plus friction jacket assembly, both they penetrate together. Mechanism, if you see in the cone penetration test, is that first only cone moves. Say let us approximately it is 40 mm. For 40 mm only cone moves. Then for next 40 mm both cone plus friction jacket assembly, both they move together. So first value you will get, that will be QC, cone penetration resistance. Second value will be cone penetration plus friction, skin friction, side friction, both combined. So if you subtract the second value, first value from the second one, you will get skin friction resistance. So skin friction load plus point load, both you can get from this. So this first we will use this QC. So QC value we have calculated. Let us say our load will be transferred up to 10 meters. So we will start the test from the ground level, say. So values which will be along the pile length, they will be used for skin friction load. Similarly, cone resistance values for base resistance. So QC values we have, we will calculate similar to earlier case. We were having NM, then NM was converted to N160. Similarly, here we convert QC to QC1N. that is CQ into QC upon PA. This PA is again 100 kPa and QC, both should have same units. This is in kPa, then this should also be in kPa. So CQ QC upon PA. Now this CA will be calculated from this equation, PA upon sigma V0 dash raised to power n, where n is normally taken 0.5. So sigma V0 dash as earlier, effective overburden pressure kilonewton per square meter, PA 100 kPa atmospheric pressure. So CQ we will calculate, but CQ value is limited to 2 for shallow depths. If it value comes out to be more than 2, then we will take 2. The value of exponent n is dependent on the grain characteristics of the soil. The value of n ranges from 0.5 for clean sands to 1 for clays. So normally for sands 0.5. Here we have again this curve is available for calculation of CRR. We calculated QC1N. QC1N we have calculated. From QC1N again we will convert that value to QC1N CS. We will convert that to clean sand. Earlier we converted our N160 to N160 CS. Similarly, in this case, we will convert QC1N to QC1N CS. Then we will see this curve. So, how to convert QC1N CS? Actually, these are the equations we can directly use if we are not to use the curves. From the curves, these equations have been derived by approximate analysis. QC1 and CS we can see from this curve also, or we can see those values from these equations. Okay? We can calculate the values from these equations. If QC1 and CS is less than 50, this equation will be used. If it is between 50 to 160, this equation will be used. So, how to convert QC1N to QC1N CS? For conversion of QC1 and CS, CN to CS, we will multiply it with Kc. Kc is CPT correction factor. This Kc is given by this equation, 0.403 IC raised to power 4, 5.58 IC cube minus 21.63 IC square, 33.75 IC minus 17.88. This equation will give you Kc. That Kc you will use here for calculation of QC1 and CS. Now, what is this Kc? How to calculate Kc? For Kc, we need IC. IC is used in this. In this equation, IC has been used. So, we will calculate IC. IC is soil behavior type index. This soil behavior type index we will calculate using this equation, 3.47 minus log Q plus 1.22 log F whole square and whole raised to power 0.5, where Q is normalized correction resistance. This will be calculated using this equation. QC value known to you, sigma V0 known to you, total overburden. This is effective overburden sigma V0 dash, PA atmospheric pressure 100 kPa raised to power n, and in this you have used Q and F also. F will be Fs over QC minus sigma V0 into 100. Now this Fs, from where this Fs will come? Again from cone penetration test. Cone penetration test I told you, first penetration that will give you QC. Then both friction jacket assembly plus cone they will move in the second stage. Difference of the two values that will give you skin resistance. From that you will calculate, difference will give you Fs. So Fs will be used in this equation. Now you will calculate F from this QC is known, sigma B0 known, Fs is known, all parameters are known. Now you have Q and F value, substitute Q and F value in this, you will get IC. Once you get IC, then if IC is more than 1.64, then this equation is used. If IC is less than 1.64, then Kc is simply taken 1. So substitute Kc value in this, you will get QC1 and CS. Once you have QC1 and CS, then from the curves or using equations, you can calculate CRR. CRR you can calculate. CSR, same equation which we have used earlier. CSR you will use same equation. This equation, CSR will be calculated using the same equation. CRR from cone penetration test, from these curves, we will get CRR. Then similarly, CRR divided by CSR, that will be factor of safety. If factor of safety is less than 1, then liquefaction is expected to take place. If it is more than 1, then liquefaction is not expected. Okay. There are some correlations also between static cone penetration and N160, QC1 and N160. If you perform one test in the other value, you can get some correlations. Some people, they have given some correlations like this, N160 and QC1 and values, some correlations are given. Now evaluating the liquefaction potential by shear wave velocity. Another method is by shear wave velocity. Normally, standard penetration test, here we normally perform standard penetration test or cone penetration test. Sometimes shear wave velocity test is also performed. Shear wave velocities are determined in site using low strain measurement schemes such as seismic refraction, downhole or cross-hole surveys. The limitation of the method is that liquefaction phenomena is a large strain event. Whereas these tests which we are performing, they are low strain measurements, based on low strain measurements, whereas earthquake is large strain event. So error will be there definitely. So that's why not very popular method. Normalized shear wave velocity Vs1. Normalized shear wave velocity Vs1 is obtained from the field measured shear wave velocity Vs by this equation. As earlier, similar steps are there. So we have Vs. Originally we were having Nm, we converted to N160, then N160 Cs. Similarly, Vs, shear wave velocity from the shear wave test in the field, then converted to Vs1 by this equation, Pa upon sigma 0 dash raised to power 0.25. So CRR 7.5. So that will be applicable to cone penetration test also, that those curves, they are for 7.5 magnitude earthquake. So if your expected earthquake is of different magnitude, so it will be value will be multiplied with MSF, magnitude scaling factor. So similarly, this equation is for CRR 7.5. A Vs1 upon 100 plus B Vs1C minus Vs1 minus B upon Ps1C, where Vs1C is critical value of Vs1, which separates contractive and dilative behavior. A and B, they are curve fitting parameters having values 0.022 and 2.8 respectively. So A and B values have been recommended by researchers like this for 7.5 magnitude earthquakes. And Vs1C critical values we can take approximately from this. So now rest is same, then you can calculate factor of safety against liquefaction as earlier. So these three methods for sand: liquefaction of clay soils, Clay soils would be considered liquefiable if all the following criteria are met. Weight of soil particles finer than 0.005 mm is less than 15% of the dry weight of soil. Second is liquid limit by Atterwork tests of the soil less than 35%. Moisture content of the soil less than 0.9 times the liquid limit. Clay soils not meeting all of these criteria may be considered to be non-liquefiable. So normally that liquefaction problem is faced in loose or medium sands. Now we will talk about earthquake induced settlements. Tendency of sands to densify when subjected to earthquake shaking. That is well documented. Subsurface densification is manifested at the ground surface in the form of settlement. Earthquake-induced settlement frequently causes distress to structures supported on shallow foundations, damage to utilities that serve pile-supported structures, and damage to lifelines that are commonly buried at shallow depths. Dry sands, now earthquake-induced settlement for dry sands. Dry sands densify very quickly. Settlement of dry sand deposit is usually complete by the end of an earthquake. And settlement of saturated sand deposit requires more time. Settlement can occur only as earthquake-induced pore pressures dissipate, because immediately due to earthquake there will be sudden increase in pore water pressures. So that depends upon drains provided, length of drain, if there is dissipation of earth pressure in small time, then settlement will be in small time. Otherwise settlement will take more time. Time required for this settlement to occur depend on permeability and compressibility of the soil and on the length of the drainage path. It can range from a few minutes up to about a day. Now, estimation of earthquake-induced settlements of sands is difficult. Errors of 25 to 50% are common in static settlement predictions. So even less accuracy should be expected for more complicated case of seismic loading. So settlement calculation definitely will have great errors. Now earthquake-induced settlements in dry sands. Densification of dry sands subjected to earthquake loading, that depends on the density of the sand, amplitude of cyclic shear strain induced in the sand, and number of cycles of shear strain applied during the earthquake. It will depend on these factors: density of sand, amplitude of cyclic shear strain, and number of cycles of shear strain applied. So at any given depth, effective shear strain, gamma effective, may be estimated by this relation. Gamma effective is, what is gamma effective? Effective shear strain. So shear strain, what is tau average? Average cyclic shear stress. Stress upon strain is modulus. So G effective is effective shear modulus. So tau average upon shear modulus, that is shear strain. So gamma effective is tau average upon G effective. So this is shear stress and this is shear modulus. You will get shear strain. Tau average over G effective. We can write it like this, dividing numerator and denominator with G max. G max is shear modulus at low strain level. G max is shear modulus at low strain level. So we will write it G max. We have introduced G max in this because curves which are available, they are in terms of that. So tau average upon G effective is this, by definition, gamma effective shear strain you can write it like this: tau average upon G max divided by G effective upon G max. Okay. Now tau average you can calculate from this equation: 0.65 A max upon G sigma V0 RD. All terms we have used earlier. 0.65 A max upon G. Here this A max, if earthquake expected is say 0.3 G, so then here we will write 0.3 G in this equation. G will cancel. So 0.3 and sigma V0 total overburden pressure. Sigma V0, this is actually sigma V0 dash, I think. So equation now this becomes gamma effective G effective upon G max equal to, now if we combine equation number 1 and 2, you will get gamma effective into G effective upon G max equal to 0.65 A max upon G sigma V0 RD over G max. Equation number 1 जो हमने लिखी, this equation, from this equation we will get gamma effective G effective upon G max, we have shifted to the other side, so 0.65, this equation you will get. Here sigma V0 and G max, they should have same units. Now G max can be calculated by the relation given by Seed and Idris. Seed and Idris, they have done lot of work on earthquake geotechnical engineering. This equation will give you answer in pounds per square feet. G max you can calculate from this equation. This actually 20,000 if used, answer will be in pounds per square feet. Sigma m dash is effective stress on the soil at the given depth in pounds per square feet. Now having computed gamma effective G effective upon G max, now curves can be used. Curves are available, these curves are there. Gamma effective G effective upon G max you have calculated. Corresponding to that you can calculate gamma effective. Effective shear strain you can calculate from this. So directly from definition you will not be able to get, only using these curves you can calculate this effective shear strain. For calculation of effective shear strain, first we have calculated this gamma effective G effective upon G max. Then whatever sigma m dash value you have, you will select that curve. Corresponding to that you can calculate this gamma effective strain. Now knowing effective cyclic shear strain gamma effective from those curves, volumetric strain epsilon c can be estimated by using another set of curves given by Tokimatsu and Seed in 1987, which are representative of magnitude of 7.5 earthquake magnitude only. These curves are available. From these curves, cyclic shear strain, and on other side we have volumetric strain. Cyclic shear strain you have calculated from the previous curves, gamma effective. Now corresponding to that gamma effective, if you know these relative densities, then you can use this set of curves. If you have n values, then you can have this set of curves. If you have performed SPT in that area, n value you are having, then you can select, let us say n value, n1 is 20, then you will choose this curve, and this you have calculated. Gamma effective is this gamma cyclic. From this you can calculate this value. This will be gamma epsilon c. Epsilon c is volumetric strain. From this volumetric strain you can calculate settlement. Again conversion factor is there, because all those curves they are for an earthquake of magnitude 7.5. So if your area earthquake expected is different from that, then your epsilon c value which you have calculated from the curves, that will be converted using these factors. Following the experimental results of Pike et al. 1975, the effect of multi-directional shaking is accounted for by doubling epsilon Cm. Pike has further suggested that multi-directional shaking, if we are to count for, then whatever value we have obtained from those curves, we will double that value. We will multiply it with 2. So epsilon C, which you have calculated, we will multiply it with 2. So to actual we will consider as 2 into epsilon C. So amount of settlement due to earthquake shaking may then be obtained by multiplying the corrected volumetric strain by the thickness of the sand layer. For if let us say sand layer thickness is 2 meters, 3 meters, whatever, so we will multiply with that. Similarly, one example I have given, settlement of say 15 meter thick deposit of loose sand with an average corrected SPT resistance of 9 was estimated for an earthquake of magnitude 6.75 by Takematsu and Seed. Maximum ground acceleration is expected to be 0.35 G. Let us say this data is there. Then what we will do, we have different sand layers, say first layer 3 meters, different layers. Okay. So gamma of different layers, then N160 for different layers. Here I have taken 9 only, but for this layer it may be 9, for this layer may be 11, 12, 15, different values of N may be there. So we will calculate sigma m dash or sigma 0 at the center of each layer. At the center of each layer we will calculate gamma into Z, effective overburden pressure. G max will be calculated using the equation 20,000 N160 raised to power 1 by 3 sigma m dash raised to power 1 by 2. So we will calculate G max. Now after calculating G max, gamma effective, G effective upon G max. This we can calculate as we have written, equation number 2 we have written. So from that we will calculate. Then gamma effective we will calculate from the set of curves, first set of curves जो मैंने आपको अभी these curves, gamma effective, G effective upon G max you will calculate, from that corresponding to the curve, your curve selected based on sigma m dash, you can calculate this gamma effective. So gamma effective from that figure, then epsilon C from the next set of curves corresponding to gamma, you can calculate epsilon C. Epsilon C for that will be for an earthquake of magnitude 7.5. Then epsilon C for our case magnitude, we will multiply it with 0.85. Then it will become corresponding to earthquake of magnitude 6.75. Then Pike et al. Recommendation to consider multi-directional effect, we will double the value. So this epsilon C will be multiplied by 2. Then settlement will be thickness multiplied by this value. Okay. So total settlement, if you have consider all the layers, then you will add up all, that will be total settlement. Another approach is Takematsu and Seed approach, post-earthquake densification of saturated sand, that is influenced by density of, that was for dry sand. Now for saturated sand, maximum shear strain induced in the sand and the amount of excess pore pressure generated by the earthquake, laboratory experiments have shown that the volumetric strain after liquefaction varies with relative density and maximum shear strain. And Takematsu and Seed used correlation between N160 and relative density and an estimate of shear strain potential of liquefied soil from N160 and cyclic stress ratio to produce chart that allows the volumetric strain after liquefaction in M7.5 magnitude earthquake to be estimated directly from cyclic stress ratio and SPT resistance. For earthquakes of other magnitudes, equivalent stress ratio can be determined. These curves have been provided. We will perform SPT as earlier. From SPT data N160 you have corresponding to N160, you can calculate CSR M7.5, CSR M7.5 and N160, and corresponding to that, wherever your point falls, you can calculate volumetric strain. Clear? N160, you have performed SPT, you have N160, you have CSR M7.5 as we have calculated earlier, liquefaction potential based on SPT. CSR M7.5 you have calculated value, N160 you have value corresponding to these two. Suppose your point lies here. So approximately we can calculate volumetric strain. So that volumetric strain multiplied by thickness of sand layer, that will give you settlement. Similarly, one example, let us suppose this 10-meter loose sand layer is there. If we are to calculate for 2 to 4 meters, let us say n value is 6, then next 4 to 6 meters n value 7, 6 to 8 meters we have different n values, then we will calculate N160. These n values are measured n values, nm which I have written. So then multiply with correction factors N160, then you will calculate CSR. Then from the curves corresponding to N160 and CSR, these curves corresponding to N160 and CSR, you can calculate epsilon C. Then multiplying with thickness of clay layer, thickness of sand layer, you can calculate settlement. Similarly, now another approach is Ishihara and Yoshimin approach. They have also given some curves which are used to calculate post liquefaction volumetric strain. Settlement will be layer thickness into strain. These set of curves they have developed. Post liquefaction volumetric strain and factor of safety which you have calculated. Factor of safety, and these curves are for N120, QC1 110. If you have performed SPT, you have N values. If you have performed cone penetration test, you have QC values. Accordingly, you will select the curve. Factor of safety you have calculated. Factor of safety and corresponding curve, whatever value you will get, that will be post liquefaction volumetric strain. So post liquefaction volumetric strain multiplied by thickness, that will give you settlement. So these are some methods for liquefaction induced settlements, and I have talked about some methods for liquefaction potential calculation. That's all from my side. Okay. Now, if you have any question. Yes, sir. Normally these are for earthquake related. All these corrections are applied. Otherwise, we apply two corrections to SPT values: liquefaction for overburden correction and dilatancy correction. Only two corrections normally we apply. But for earthquake purpose, well, if you are to calculate liquefaction potential, then we need to apply all these corrections.
Because you are correcting for N60, you also need an energy measurement for the SPT.
That correction has been applied only because with that correction.
Because without energy measurement, you cannot calibrate it to N60.
No. Actually, energy measurement.
Yes, energy measurement is required. Because either way, suppose SPT is being done in the field with the automatic, and transfer will be more than 60. Or it is being done by the manual method, it will be less than 60. So in that case, we need energy measurement.
So see, it is not necessary that 100%, 60% you will get. some approximation is always there. Actually, in dynamics, so many approximations are there. I already told you that results, we can't say they are error free. These are all based on experiments. Most of these curves, they are based on experiments, not scientific theory. Sir?
We can do, sorry, I'm losing my voice. We can do one thing. Pick SPT profile from any one site, or even make one up. Yeah? Estimate uh, the liquefaction potential and settlement from that. You also mentioned you can convert that SPT into QC, the correlations.
Yes, sir.
Use those correlations, get the QC, and do the same calculation again. Use the VS correlation and get the settlement by that method. Then you can see what is the error band by doing that. Maybe we should set it as a
actually those correlations, but those correlations, they are also based on experiments.
Yeah, but what is the error in the correlation? That's what you will get.
But
so
error,
one method gives 1 meter settlement, the other one gives half a meter.
then I think, sir, we should not use correlation. We should perform both the tests. Then we can compare.
Yeah,
If we compare the results with the correlations, both the tests we perform, only then some error will be detected. If we use only correlations for calculation of QC from n value, then error will not be detected, no? Because that is based on n value only.
But
so if we perform both the tests,
I don't think.
And then answer will not be same, because that is a great approximation will be there. Actually, these methods are very approximate methods, very approximate methods.
In SPD, there are more corrections.
Yes.
CPT is why that's why we prefer CPT because
Actually, energy measurement is rarely done in the field.
SPD is the best should not be.
Actually, in India, mostly people depend on SPD.
SPD code of India now they specify the energy. Recently released.
Yes.
Graph of calculating shear strain effective with respect to shear strain effective G effective by G. In this
one?
Yeah. In this graph, that 15 cycle is mentioned. What is that, sir? 15 cycles of that?
15 cycles of.
If there are 10 cycles, 20 cycles.
Then this is for 15 cycles.
This is for
These curves are for 15 cycles. No other curves are available. Only the people Takimatsu seed eater, only 2-3.
It's done in 87.
Yes.
And that's the only link we have to campus.
Yes. There actually, most of people, they have not worked on this. Very few people. Takimatsu seed eater, you will see same names will be there.
It's Tokimatsu, not
Tokimatsu.
Koji. KOHJ.
So must be. Okay. It is Tokimatsu.
I think he's the last POC after the seed died.
So seed died?
After the supervisor.
Okay. Okay, thank you.
Okay.
Then tomorrow at 9:30? Huh?